Hi guys, welcome to my IGCSE Edexcel all-in-one physics video for the new specification 9 to 1. I'm so excited that it is here. Now these are my incredibly detailed videos where I try my absolute best to hit every single specification point. As we go through, you'll notice my perfect answers popping up. These are the exact phrases I think you should be using in the exam. Don't forget you can purchase my perfect answer revision guide on my website, which is www.sciencehazel.co.uk, which you can see here, or you can click here, and you'll find details about private tuition, and if you want to attend any of my revision courses, this is where you need to go. However, it is about time we got started.
Now we're going to take a look at the speed, distance, time topic. So there are some very key equations that you need to be aware of. So you know me, I love formula triangles. So I'm going to have my first one here, which is D at the top, then S, then T. Now you cover whatever it is that you're after. So I'm after distance. So if I cover that over with my thumb, I can see that it's therefore speed times time. If I'm after speed, then we're going to do distance divided by time. And then lastly, time is distance divided by speed. So if they ask you for the equation, sure, use your formula triangles to actually work out what the equation is, but you must write out the full equation to get the mark. Formula triangles do not count. So as you can see on the left-hand side, I've drawn very poorly a distance time graph, and I'm after the speed at point A. So to work out the speed, I know that I need to do distance divided by time. I can read that straight off the graph, so I can see that the distance travelled is 8. The time was 4 seconds, so simple calculation. The speed is therefore 2 meters per second. Meters per second due to the units we can see on the y-axis, which was that distance was given in meters and time was given in seconds. It's important to understand these graphs fully because they could ask you, for example, how long was the car stationary for? So in terms of stationary, you're looking at the flat parts of the graph. So the car is stationary here. Why? Because it remains at 8 meters throughout that time. So how long was the car stationary for? Have a look along here. And the answer here is 4 seconds. This is a different type of graph. So the velocity time graph, or the speed time graph, not to be confused with the distance time graph. So we are being asked to find out the acceleration at point A on the graph. So acceleration is given by the equation acceleration equals final speed minus initial speed over time. And a neater way to write that is A equals V minus U over T. So looking at portion A of the graph, what is the final speed? Well, it's given here. So read across and you'll see that it is 5. The initial speed is given here, and we know that's 0, so 5 minus 0. The time taken was 4 seconds, so the answer here is 1.25. Now be careful with your units, you're looking for meters per second squared for acceleration. Another thing they like to ask you is to calculate the distance travelled. Now this is a longer task, and remember distance travelled is given by the area under the graph. So let's calculate the entire distance travelled by this particular vehicle. So the way I like to do this is by splitting it up. You can work it out as a trapezium, or you can work it out as 2 triangles and a rectangle, which I personally find easier. So I'm going to label them A, B and C. So area A is given by this formula. Well, it's a triangle, so I need to put in a half immediately. Times it by the height of the triangle, which is 5. Times it by its width. Do the calculation, and that will therefore be 10 meters. Area B is more straightforward, it's just a rectangle, so just make sure you're reading the correct lengths. So it's 5 again, this time times it by 3, you get a value which is 15 meters. Finally, area C, we're back to our triangle, so we need a half, times the height of the triangle, which is 5, times the width of the triangle, which is 2, so we get 5 meters. If you add that up, you get a total area of 30 meters, and that therefore is the distance travelled. (9.6) By measuring the length of the skid marks, an accident investigator determines that the distance a car travelled between the brakes being applied and stopping was 22 meters. The investigator used a sled to determine the friction. The investigator then calculated that the car decelerated at 7.2 meters per second squared. Calculate the speed of the car just before the brakes were applied. Give your answer to 2 sig fig. Okay, so this is SUVAT. So we're using this equation, which is v squared equals u squared plus 2as. And now it's just a matter of identifying what everything is. So the distance here is s. The acceleration is, well, it's minus 7.2, but that's the acceleration. So that's a. We're looking at the speed of the car just before the brakes were applied. So we're looking for the initial speed, which is u. So that's a question mark. And we know that it stopped. So that means the final speed was 0. So just substitute in all these values. So it's literally 0 squared, which is 0, equals u squared plus 2 times minus 7.2 times the distance, which was 22. So 0 equals u squared minus 316.8. How do we get u squared by itself? Well, add it to both sides. So 316.8 equals u squared, and then square root that answer in order to calculate your u. So u will equal 18 to 2 significant figures. I've picked out some questions. So question 1, a toy car rolls down a ramp and hits a cushion. The graph shows how its velocity changes with time. So this is effectively a speed time graph. Constant velocity on the graph is shown by, what does the word constant mean? Well, it means same. So where on this graph is it the same velocity? Now you can kind of imagine a y-axis and the numbers going up the y-axis. So it could be something like 0, 10, 20, 30. On the velocity front. So where does that not change? Well, it's obviously going to be the horizontal portion of the line, because at that point the speed or the velocity is going to be the same everywhere. So the answer here is B, the horizontal part of the line. And with these sorts of questions, rather than reading the options through and getting confused, I would look at the question first of all, work out what you think is the answer, and then see if that is an option below. The distance travelled is shown by, well, again, I told you to work out distance, it's the area under the graph line. Let's look at the options, and that's A. The average velocity of the toy car is given by, so remember your equation, velocity or speed equals distance divided by time, therefore that is B. A bus travels along a straight road. The graph shows how the velocity of the bus changes during a short journey. Okay, so we've got a velocity time graph, so again, distance will be given by area under the curve, acceleration will be given by the gradient. Anyway, state the velocity of the bus after 25 seconds. So you're looking up here. The answer here is 6 meters per second. How long is the bus stationary during its journey? Now, I've seen loads of people get this wrong because they think that it's stationary here and here. Well, no, that's absolute rubbish, because look at the velocity. It's 12. So stationary means that it was standing still. So standing still means that the velocity must have been 0, which is just this chunk here. And therefore your answer here is 10 seconds. State the equation linking acceleration, change in velocity and time taken. They're giving you the exact wording, so you want to write it out as they've written it. So you're going to write acceleration equals change in velocity over time taken, or you could have written A equals V minus U over T. Calculate the acceleration of the bus during the first 10 seconds. Give the unit, that's worth 3 marks. So we'll have a look back up here, and we're looking at this portion of the graph. The first 10 seconds, we're looking at the gradient. So that equation was acceleration equals V minus U over T. So that is final speed, which is 12, minus initial speed, which was 0, over time taken, which was 10. So 12 take 0 over 10 is 1.2. The units of acceleration are meters per second squared. State the equation linking average speed, distance moved and time taken. Average speed equals distance moved divided by time taken. The bus moves a total distance of 390 meters during the journey. Calculate the average speed of the bus. So speed equals distance divided by time. Distance is 390 divided by, look on the graph for whatever the time was, and it was 60 seconds. Pop that into your calculator and your answer will be 6.5 meters per second. The bus travels further in the first 30 seconds of its journey than it does during the last 30 seconds of this journey. Explain how the graph shows this. Well, remember that I told you distance is given by area under the graph line, and you can see that the trapezium for the first 30 seconds is way bigger than the one for the second 30 seconds, so therefore clearly the bus travelled further. So for the first mark, state the fact that distance is given by area under the graph, and then for the second mark, compare the two areas under the line, and you're done. Question 4. The diagram shows some people waiting in a queue at a supermarket. The queue moves forward each time a person leaves the checkout. Person X spends 7 minutes in the queue before reaching the checkout, and the graph shows how distance changes with time for person X. So it's the last person in the queue, and notice that it is a distance time graph. So what is the initial length of the queue? And we're looking for that in meters. So all you have to do is read off here on the y-axis. So read along and you'll see, if my pen wasn't as fat, that it is 6.1 meters. Explain how you could use the graph to work out the number of times person X is stationary. So explain is going to be a very crucial word here, and we also need to work out the number of times the person is stationary. So stationary means that they don't move. So when aren't they moving? Well, it's all the flat portions of the graph. So that's 1, 2, 3, 4, 5, 6, 7. So you're going to say 7 times that they were stationary. And we know this because the flat part of the graph indicates 0 speed. State the equation linking average speed, distance moved and time taken. So out of the way, I'm going to write my formula triangle dst. So therefore average speed equals, cover the s, distance moved over time taken. Part 2, calculate the average speed of person X in the queue, give the unit, don't forget to give the unit. So the distance moved, we know, is 6.1 meters. The time is 7 minutes. Don't get caught out here. I know the graph looks confusing, but it tells us up here that the person spent 7 minutes in the queue. I'm going to multiply it by 60 because the SI unit for time is seconds, so obviously there are 60 seconds in a minute, hence why I'm timesing it by 60. Pop that into your calculator and you'll get a value which rounds to 0.015 to 3 significant figures, and we know that the distance was in meters. I've already told you that I've converted to seconds, which is why the unit here is meters per second. We now need to discuss the difference between weight and mass. So people constantly get this confused. They talk about how much they weigh when actually they're talking about their mass, and I'm going to explain what I mean by that. So weight, first of all, is given by the unit N, which stands for newtons. Mass is given by the unit kilograms. And so straight away we can see that they have different units. Now it's worth noticing that your mass is unchanged. It doesn't matter where you stand, which planet you're standing on, where you are in space, your mass will remain the same. So if your mass is 50 kilograms on Earth, it will be 50 kilograms on Mars. And that's because it's really a description of what you're made up of. However, with weight has to take into account gravity. And therefore, when gravity changes, your weight will change. If we look at the equation linking the three, you find that weight equals mass times gravitational field strength. So if you have a mass of 50 kilograms, you're standing on the Earth, which has an approximate gravitational field strength of 10, your weight will therefore be 500 newtons. So this would be the case on Earth. However, on the Moon, if we do the same calculation, we find that although your mass is still 50, your gravitational field strength is hugely reduced on the Moon to, in fact, only 1.6, meaning that your weight on the Moon is only 80 newtons. So this is a huge change. Your weight has drastically decreased on the Moon, whereas your mass has stayed the same. So although in everyday life we talk about how much we weigh, we say 50 kilograms, remember that's inaccurate and that we're actually discussing our mass. And as long as you can use this equation, weight equals mass times gravitational field strength, you'll have no problems. We now need to look at the topic of force. So just remember first of all the effect that a force has on an object, and that can be that the force changes the object's speed, it can change the object's direction, or it can indeed change the object's shape. You need to be able to list the different types of force, so I've written them out here, and now we just need to have a quick chat about what all of those things mean. So first of all, notice that some of these forces are contact forces, and these are forces which act between two objects that are actually physically touching each other. Non-contact forces is obviously, as the name suggests, when they don't touch. So let's actually have a look at this normal reaction first of all, because that's quite a strange one. This normal reaction force or normal contact force, it's all the same thing. That's when an object is on the ground and it experiences a force which is perpendicular to the surface. And what that means, that's where the word normal comes from, because remember in the light topic, a normal line is a line, for example, drawn like this. So here's your glass block, and here are some normal lines because they're 90 degrees to the surface of the glass block. So in a similar way, the reaction force is felt perpendicular to the surface. And I'll show you an example of that later with a car, so don't worry too much now. Friction is a nice straightforward one. That's when two objects slide past each other, they experience a friction force. So for example, a toy car sliding down a slope will experience friction where its wheels touch the slope. Air resistance or drag, that's to do with objects moving through the air, so it could be a car being driven along the road, and air particles collide with the car, creating a small force which acts to slow it down. The faster the car is travelling, the more particles that will hit per second, hence air resistance increases, and that's why things like cars have to be streamlined to reduce air resistance. Looking at non-contact forces, so let's start with the magnetic force, and that is experienced by any magnetic material inside a magnetic field. Do remember that opposite magnetic poles attract, so north and south poles will attract. Like poles, such as two north poles or two south poles, repel. An electrostatic force is all to do with static charge, so we're talking about the build-up of charge, and it's experienced by any charged particle that's held within an electric field. So a gravitational force, as the name suggests, is to do with gravity, and it's experienced by any mass which is found within a gravitational field. And remember, these masses may be attracted towards each other due to this gravitational force. The easiest example here is the Sun and the Earth. They're both masses, they're both very large objects, and they're held in position due to the gravitational force between them. Weight I've already touched upon. Remember, that is a force acting downwards from any object, and it incorporates both the mass and gravitational field strength. Upthrust, this is when we're talking about water. So for example, a boat sitting on water, although its weight is acting downwards, there's the force of the water pushing back up, so it's the equivalent of the normal reaction force, so we call this upthrust. And if weight and upthrust are equal, then we know the boat will float. The nuclear force is, as the name suggests, to do with the nucleus of atoms, or the nuclei of atoms, and it's the strong attractive force between the protons and the neutrons within the nucleus that helps hold the nucleus together. Remember that force is measured in newtons, and that you'll often see a force diagram, and that's basically an object which is moving, and it will have arrows, and the size of the arrow represents how large the force is. So obviously the larger the arrow, the larger the force. Remember, in your textbook, I'll often talk about balanced forces. That is when two forces acting on an object, they'll be acting in opposite directions to each other. And remember that they have to be the same size for them to be balanced forces. And that basically means that an object which is standing still, i.e. stationary, it won't speed up, it will stay exactly as it is. And it also means that an object which is travelling at a certain speed, when it has balanced forces acting on it, will continue to travel at that speed. It won't speed up, it won't slow down. So therefore, if we're talking about unbalanced forces, it makes sense that one of the forces opposing the other force is larger than the other. So if the object is stationary, it will start moving, and if the object is travelling at a certain speed, it will either speed up or slow down. So what are these forces that we're talking about? I'm going to use the example of a car driving along the street to help illustrate this. So you have a car, it's sat on the tarmac and it's driving. So the forward force is going to be the driving force from the engine, and that will be causing the car to either accelerate or just carry on travelling at the same speed. Opposing that driving force will be several other forces.
First of all, air resistance, otherwise known as drag. Now what is that? Basically, if you've got a car moving, you've got air whistling past it, and these air particles, they'll collide with the car and they generate a tiny, tiny force which acts in the opposite direction to the direction the car's travelling. And by doing that, they oppose the motion of the car, so they act to slow it down. We have lots of other forces opposing motion, so there's friction. Remember, friction is the force that occurs between surfaces, so the friction in this example will be between the car wheels and the road. So remember, it's that friction which is useful because it allows the car to grip onto the road, and in certain conditions like icy conditions, wet conditions, or if the tyres have been too worn, you'll decrease the friction between the tyres and the road, and that can lead to dangerous occurrences like the car skidding. So a bit of friction is important. You have other forces acting on the car. You have weight. Remember, that's the downward force due to gravity. And don't forget this force, it's called the normal reaction, and that occurs between the tyres and the road surface, and it occurs upwards, so perpendicular to the road. And basically all the normal reaction is it's the force which stops objects kind of being forced into the earth, so it acts against gravity. That's quite a hard one to imagine, but just remember that it occurs at 90 degrees to the surface. Remember, when we're talking about terminal velocity, we tend to use the example of a parachutist jumping out of an aeroplane, and you'll often see lots of diagrams of arrows of different sizes. I'm going to try and talk to you about that now. So let's start at the top. We're starting in our aeroplane and our parachutist is looking out and he's about to jump. The moment he jumps, the only force acting on him is weight. So that will cause him to accelerate towards the Earth's surface. Now, the faster he accelerates, the bigger the air resistance, because remember, as he's dropping, he's going to be hitting lots of air, and those air particles are going to be acting in the opposite direction to his motion, trying to slow him down. And the faster he travels, the more particles will be hitting per second. So the overall force of drag or air resistance will become very large. So at a certain point, you will find that the size of the air resistance or the drag will match the size of the weight force acting downwards. And we call that terminal velocity, because all that means is that the two forces are balanced and the parachutist will no longer accelerate. He'll just continue falling at a constant speed, and that is what terminal velocity is basically, neither accelerating or decelerating, just travelling at a constant speed. Before too long, the parachutist will choose to open his parachute because he won't obviously want to splatter on the ground. When he opens his parachute, you see a massive increase in the surface area of the parachutist, and therefore way more air particles will be trapped inside the parachute, and therefore air resistance will increase hugely, and he'll jerk upwards as a result of that, and you'll see that he'll slow down. However, because his speed decreases, that actually causes air resistance to decrease, because if you think about it, the slower he now travels, the fewer air particles will be hitting him and opposing his motion, and therefore he'll slow down. And eventually his weight and the size of the drag air resistance force will become the same, and we call that terminal velocity again, because he's now travelling at a constant speed. Now remember, that terminal velocity will be at a much lower speed than the initial one, and that's due to the fact he's opened up his parachute.
Another physics equation you need to be aware of is FAM. So F stands for force, A stands for acceleration, and M stands for mass. So let's work out the various variations. So force equals, we can see that it's acceleration times mass. If we're after acceleration, cover that up. You can see that it is force divided by mass. And lastly, mass equals force divided by acceleration. Touching quickly on the units, mass should always be in kilograms, force is newtons, acceleration is meters per second squared, so make sure you have that sorted, and we'll look at a couple of examples now. So in this question, we're calculating the resultant force required to accelerate a 30 kilogram object at 1.5 meters per second squared. So yeah, we have mass, we have acceleration, we're looking for force, so force equals acceleration times mass. is the simple expedient of substituting in those values, so 1.5 times 30, which gives you a value of 45 newtons. Question 2. The force on a moving object is 1000 newtons. Calculate the mass of an object if it is accelerating at 2.5 meters per second squared. So we've been given the force and the acceleration. Mass is given by F over A. Our force is 1000 newtons divided by the acceleration, which is 2.5, giving us a value which is 400. Don't forget your units. It is in kilograms. A student investigates terminal velocity. She uses a tall glass tube filled with oil. She drops a metal ball into the tube and the ball falls through the oil. Use ideas about forces to explain how a falling object can reach terminal velocity. It doesn't matter what this question is. If it's someone jumping out of a plane or a ball being dropped into a tube of oil, if it mentions terminal velocity, this is your perfect answer. So first of all, you want to state that the ball has a weight, and that will be its downward force. Acting upwards will be the force of drag. As the ball accelerates, the drag force will increase and eventually the weight will equal drag. At this point, the ball no longer accelerates, it travels at a constant speed and there is no further acceleration, and this means that terminal velocity has been reached. So that's your perfect answer. Try and write it in sentences. I've written it like that for ease of iPad use. Describe how the student could find out if the ball reaches terminal velocity as it falls through the oil. In your answer, you should include the measuring instruments that the student will need, the measurements she should take, and how she could use her measurements to find out if the ball has reached terminal velocity. You may include a labeled diagram in your answer. So clearly, we need to use a timer to time how long the ball falls for, and we need to use a ruler to make sure that the ball is falling over the same distance every time. In terms of the measurements taken, you need to take a measurement of time for the amount of time that it took for the ball to pass between 2 points. You obviously want to work out that distance using your ruler, and then repeat and calculate an average to increase the reliability. To make it even more specific, you could have used a light gate. And then lastly, once you've worked out the distance and the time, you can obviously calculate speed using speed equals distance divided by time. So I want to quickly talk to you about Hooke's law. Now, Hooke's law is a pretty boring experiment whereby a guy called Hooke, amazingly, originally hung various weights off a spring and measured the new length of the spring. And then obviously as more weights were added, the spring got longer. And then he plotted a graph which was force, and it's okay to plot force because remember force and weight have the same unit, which is newtons, against the extension. And you see on the graph that it should be a proportional relationship, which means that as the weight increases, the length of the spring increases, which makes sense. Then you'll find that the line distorts, and that's because we're no longer increasing proportionally, and that's because the elastic limit of the spring has been reached. It's deformed, it's bent out of shape, and it won't return to its original length. So that's what underpins Hooke's law. Now we're going to look at a past exam question on it. So a student investigates whether a spring obeys Hooke's law. She uses the apparatus shown in the photograph. Which additional measuring instrument does the student need for the investigation? Well, I've told you it's all about measuring the length of the spring, so we need a ruler. Explain how the student can investigate whether the spring obeys Hooke's law. So we're basically looking for experimental details on what they're going to do. So first of all, you want to measure the original length of the spring using that meter ruler, and then we're going to add a known weight to that hook and measure the new length of the spring. And then we just repeat the process using a range of different weights. So we could go up to 20 newtons, 30 newtons, 40 newtons, or we could repeat at each weight, because remember, repeating, calculating an average is really important, and that's worth a mark for just pointing out that particular experimental detail. What is the momentum of a bullet of mass 50 grams travelling at 300 meters per second? So momentum is given by this equation, which is momentum equals mass times velocity. This is a nice straightforward example. The only thing to notice is you need to convert your grams into kilograms. We do that by dividing by 1000 times via velocity, which has been given as 300, and our final answer is 15. Notice the units, which is kilograms meters per second, and we can see that if we have a look at the equation, well, mass is kilograms, velocity is meters per second, so I'm just shoving them together to get my unit. Getting more difficult now. This is a recoil velocity style of question, but don't worry, I'll show you the easiest way of doing this. So in this example, Emma is standing still and fires a rifle. The bullet has a mass of 0.045 kilograms and is travelling at 350 meters per second. If Emma has a mass of 60 kilograms, with what velocity does she move backwards? So make this comment first of all. Momentum is conserved, which means it doesn't change. And because of that, you can then write this comment, momentum before equals momentum after. And we're going to use this to lay out our answer. So what is Emma's momentum before? Well, we've been told she's standing still, which means that her velocity is 0, times it by her mass, 60. We also know that the rifle hasn't done anything yet, it's going to be fired. In that case, the velocity of the bullet is 0 and its mass is 0.045 kilograms. Looking at their momentum afterwards, so her momentum will be her mass, which is 60, times her velocity, which is x, that we don't know the answer to yet, plus that of the bullet, so that's going to be 0.045 multiplied by 350, and that's a matter of sorting out that equation. So those cancel out because 0 plus 0 equals 0. We have 60x plus 0.045 times 350 to get 15.75. How do we solve that equation? Well, we take away 15.75 from both sides to get the 60x by itself. How do we make x by itself? Divide by 60 on both sides. So her velocity is minus 0.265 meters per second. In this question, a boy of mass 50 kilograms on ice skates throws a ball of 1 kilograms in front of him at a velocity of 2.5 meters per second. What is the boy's velocity? So, stating the same as usual, momentum is conserved. It's worth writing that because even if you get the calculation wrong, there tends to be a mark available for writing it. Momentum before equals momentum after. The momentum before is 0 because neither the ball or the boy has moved. The momentum after will be the mass of the boy times his velocity plus the mass of the snowball times its velocity. So cancelling down, 50x plus 2.5, take 2.5 away from both sides. And then to get x by itself, you want to divide by 50, again on both sides. So the boy's velocity is minus 0.05 meters per second, which means he's travelling in the opposite direction. Here's another type of momentum calculation. These will always be answered in the same way. If it's an object colliding with another object and they stick together, then this is the method you need to use. So in this situation, a car of mass 1,000 kilograms travelling at a velocity of 20 meters per second collided with a stationary motorbike of mass 500 kilograms. The vehicles move together after impact. That is crucial. They've effectively stuck together. Calculate their velocity. So as always, momentum is conserved. Momentum before equals momentum after. So let's have a look at momentum before. So what is the momentum of the car before? Well, it's its mass, which is 1,000, times its velocity, which we've told is 20 meters per second. The motorbike has a mass of 500 kilograms, but its velocity is 0 because it is stationary. The momentum afterwards will be their combined masses, which is 1,000 plus 500. So that's both the mass of the car and the motorbike, times their velocity, which is what we're after. So let's start sorting this all out. So that will become 20,000. 500 times 0 is 0, and that becomes 1,500x. To get the x by itself, we divide both sides by 1,500. So x is 13.3 meters per second, so that's the velocity with which they move off at. A car travelling at 20 metres per second collides with a stationary lorry and is brought to a rest in just 0.02 seconds. A woman in the car has a mass of 50 kilograms. What force does she experience? And we need a different equation this time, which is that force equals change in momentum over time. So force is what we're after, so that's x. Now the change in momentum is the initial momentum minus the final momentum. Ooh, that doesn't look like what I'm trying to write. So the initial momentum of the woman will be the velocity of the car times her mass, and that makes sense because after all she's in the car. And then we take away the final momentum. Well, it's coming to a rest, which means although her mass is staying the same, the velocity obviously reduces to 0 because the car stops. And time we've told is 0.02 seconds. Use your calculator. So 20 times 50 is 1000 minus 0 over 0.02. And therefore the force she experienced is 50,000, and the unit is a force unit, so that's newtons. 9. A student is playing a game with some empty tins. He throws a wet cloth of mass 0.15 kilograms at the tins. The wet cloth moves at a velocity of 6 meters per second. State the equation linking momentum, mass and velocity. So that is momentum equals mass times velocity. Calculate the momentum of the wet cloth and give the unit. Don't forget to do the other half of the question. So momentum equals mass, which you know is 0.15, times the velocity, which is 6. When you put that into a calculator, you'll get 0.9. And we can see that mass is kilograms, velocity is meters per second, which is why this is simply the unit. If you can't remember it, just work it out from the equation. The wet cloth sticks to tin 1. The mass of the tin 1 is 0.05 kilograms. The cloth and tin 1 move away together, calculate their velocity. So I always do this in the same way, which is momentum before equals momentum after. Now we've just worked out the momentum of the cloth, which is 0.9. Because the tin wasn't moving, it must mean automatically that its momentum is 0. And then the momentum after, well, they've stuck together, so we need to add up their masses. So that's 0.05 plus 0.15 times by their common velocity. So let's just do the maths and sort this equation out. So now we simply do x equals 0.9 divided by 0.2, giving you a value which is 4.5 meters per second. The student throws a bigger wet cloth at the remaining tins. The wet cloth sticks to tins 2 and 3 and they move away together. The student concludes, I threw the cloth the same way, so the velocity of tins 2 and 3 is the same as the velocity of tin 1. Do you agree with this conclusion and explain why? So clearly the student is wrong, and that's because the variables haven't been controlled. So the mass of the cloth could be different, the mass of the tins could be different, and the cloth velocity hasn't been measured. So try and use your common sense with this one. Time for some moment questions. The diagram shows the apparatus used to investigate moments. The 2 Newton weight is placed 60 centimetres from the pivot. The Newton meter is placed 10 centimetres from the pivot. State the equation linking moment, force and perpendicular distance from the pivot. Right, moment equals force times perpendicular distance. Remember the units. Moments are measured in Newton meters. Force is measured in newtons and perpendicular distance is measured in meters. 2. Calculate the reading on the Newton meter. Ignore the weight of the ruler. Okay, don't stress here. We can work this out. Remember the law, which is that clockwise moment equals anti-clockwise moment. So let's look at the clockwise moment. So we've been told that the weight is 60 centimetres from the pivot. The moment, therefore, clockwise will be 0.6 because you need to convert from centimetres into metres times 2. And now we need to look at the anti-clockwise moment. I can see that this Newton meter is at 10 centimetres. So it's just a matter of substituting them all into the equation and finding the missing value. And I'm going to show you what that looks like. So let's just do clockwise equals anti-clockwise. Please don't run out of space, Hazel. So clockwise was 2 newtons times the distance, which I said was 0.6. We've just seen that the Newton meter is 10 centimeters away from the stand, so that's 0.1, and we're looking for the weight of the ruler, which is the same as the force, so I'm going to write x here, and now we just need to solve. 1.2 equals 0.1x, therefore x equals 12 newtons. I'm going to chuck in a few other maths things here. So question 6, the person has a suitcase with wheels. The person pulls the suitcase with a horizontal force of 13 newtons for 110 meters. State the equation linking work done, force and distance moved. I don't know if I've told you this before, but try and remember, especially IGCSE people, remember all your equations as formula triangles, because then you won't have to learn as much. And then as soon as you get your paper, write them all down on the back, and then you can just keep referring to them, so it won't be so hard to pluck it out of your head. But for the time being, remember work done equals force times distance. So calculate the work done on the suitcase by the person. So let's just write, be good if I had the pencil, work done equals force times distance. Force is 13, distance is 110, and the answer here is 1,430 joules, because that is the units. Let's pop it here. How much energy is transferred to the suitcase? Okay, this isn't a trick question, just remember that work done and energy have the same unit, which is joules, so you can literally just copy that number down here. B, the suitcase falls over. Explain why its gravitational potential energy, it loses gravitational potential energy when it falls. I wondered where the question was there. Remember, you calculate gravitational potential energy by doing mass times gravity times height. Therefore, we know that gravitational potential energy depends on height, so there's your first mark. And therefore, as it falls, h will obviously decrease, and that's all you really need to say. C, the person starts to raise the suitcase again by pulling on the handle with force F. The weight of the suitcase is 150 newtons. State the equation linking moment, force and perpendicular distance. So remember, moment equals force times perpendicular distance. Now we need to calculate the force that the person must apply on the handle to start raising the suitcase. So remember that the clockwise moment equals the anti-clockwise moment. Our clockwise moment this time is the weight of the suitcase pulling downwards. So we're going to write, remember, moment is force times distance, so force acting clockwise is 150 times the distance, which is 0.32. We're looking for force, so I'm going to write x here, and then remember, moment is force times distance. We've been given the distance, which is 0.87. And then if I solve for x, I get an answer of 55 newtons. This is more maths. If you're not happy with how I work that out, do let me know and I'll add an extra step next time. So we're going to start by looking at the various components within a circuit. Then we're going to move on to looking at the graphs, Ohm's law, and I'm going to finish with all the calculations because there's a lot to do on that. But like I said, we're starting with the electrical components. So let's start with drawing a cell first of all. And remember, it has both a negative and positive terminal. The positive terminal is the longer line. If you have two or more cells together, such as this, you have a battery. What's lighting up inside a circuit is known as a lamp or a bulb, and we draw it using this particular symbol. Next up, we need to draw a resistor. This is quite straightforward because it is just a rectangle. Now, if you draw a rectangle, but this time draw an arrow going through it, that tells you it is a variable resistor, which means you can alter its resistance of the circuit. And then underneath, we're going to draw what I call the hockey stick component, and this is a thermistor. It is a temperature-dependent resistor. Looking at diodes now, it looks a bit like the play button. A diode is special because it allows the current to flow in one direction only, given by the direction which the arrow is pointing. This means that the current in this case is moving to the left. If we add a couple of arrows to this, it is a light emitting diode, so that's an LED, and you find those on your remote controls, for example. Next up, if we want to measure the current of a circuit, we're going to use an ammeter. If we're measuring the voltage, we're using a voltmeter. And then we can add a fuse to our circuit. Now remember, a fuse is a safety device. It melts when the current is too high, breaking the circuit. remember, if you're asked the difference or the advantage of using a circuit breaker as opposed to a fuse, is that a circuit breaker is much faster and easy to reset. Why? Because look at the fuse, the wire is going to melt, and so you're going to have to replace the whole thing before you get your circuit working again. Let's make a couple of notes on how you add various components to a circuit. So I'm just going to draw a simple circuit containing a battery and a light bulb, and now I'm interested in working out the resistance of this circuit. So remember, we're using this formula triangle, VIR. To work out resistance, you just cover the R and have a look at what's left. So it's V over I. I stands for current. It's given by the letter I because it used to stand for intensity of current. So historically speaking, we've always used I to represent it. Now, in order to work out resistance, I therefore need to know both the voltage and the current. It is absolutely essential that you know that the voltmeter is added in parallel around the component in question. That in this case will be the bulb, so you add it as an extra branch, and the ammeter needs added in series, which is why I'm going to pop it here. It doesn't really matter where it goes, but it needs to be in series. They often give you questions with various diagrams asking you what the problem is, and quite often you'll find that the voltmeter and the ammeter aren't in the correct place, so do make sure you know that. Remember, the units for resistance is the ohm, whereas for current it's amps and for voltage it is volts. Sometimes they want to know why the resistance increases when the temperature increases, and I'm just going to quickly show you why. So if I draw a wire, remember wire is made out of it's made out of metal, which is made up of positive metal ions and negative electrons. Now what happens if you heat that wire? Obviously those positive ions are going to vibrate more because they contain more kinetic energy, and therefore it's going to impede or inhibit the flow of electrons through the wire. So if they ask you why does resistance increase with increased temperature in a wire, you're going to say it's because the positive ions vibrate more, stopping the flow of electrons. Do notice, however, that thermistors behave differently. As temperature increases, a thermistor's resistance decreases, and that's because it's not actually made out of a metal. You don't need to know why, but do remember that as the temperature increases, the resistance decreases. And while we're talking about resistors, let's look at this resistor, which I've already forgotten to mention, but it's fine. This is a light dependent resistor. Now, when the light levels increase, the resistance decreases, and this is used in your street lighting outside. So as it gets dark, this light dependent resistor, this LDR, is the reason why the lights come on. There are a few graphs I want to talk through now. Now do remember Ohm's law, and that states that the current through a resistor at constant temperature is directly proportional to the potential difference across the resistor. And various components obey Ohm's law and some do not obey Ohm's law. Now a wire obeys Ohm's law, and you'll see that because you can see it's a straight line through the origin. So clearly you can see that as the current increases, the voltage increases, and that's at constant temperature. So a wire obeys Ohm's law. You get a very different shape when you show a filament bulb, so a light bulb. This is not a proportional relationship. We've got a sigmoidal shape, an S shape, and the bulb therefore does not obey Ohm's law because there's no direct relationship between the two. And then lastly, and very strangely, the diode looks like this. Again, it doesn't obey Ohm's law, and the reason it's this shape, the graph, is because the diode only allows current to flow in one direction only. We just need to discuss current and voltage rules for both a series and parallel circuit. So notice that in a series circuit, the current is the same everywhere, whereas the voltage of individual components adds up to the total voltage. And I'm going to show you what that actually means now. So I'm drawing a battery here, which let's say it has 8 volts across it. Then we've got a light bulb here, a regular resistor here, and I'm just going to complete the circuit. So if I tell you that the current here is 12 amps, because I've said that the current is the same everywhere, it doesn't matter if an ammeter got added here, here, or here. All those readings would be 12 amps. However, with the voltage, if you added voltmeters here and here, their readings would not be 8 volts. Let's say that this was 5 volts, the reading. That means that this reading here must be 3 volts, and that's due to that second point, that the voltage of the individual components adds up to the total voltage. The opposite is true in a parallel circuit. Here you find that the voltage is the same everywhere, whereas the current of the individual components adds up to the total current. That means that each of these light bulbs here will have 12 volts going through them, and that explains why with a parallel circuit, how if you keep adding extra bulbs, the brightness remains the same, and that's because they receive the same voltage. However, it will mean that your battery will run out 3 times as quickly as if there was only one. In terms of the current, pretend that was a 2 amp bulb, this was a 2 amp bulb. Well, we know because it has to add up to the total current, this lamp down here is slightly different in that it has a current of 1 amp. So a 4-volt battery can supply a current of 5 amps for 20 minutes before it needs recharging. Calculate how much charge the battery can provide before it needs recharging. At this point, what I always do is I draw out my formula triangles, because why not? It's good to get your head nice and into the question and knowing that you actually know stuff that you can use. So the first one is voltage is current times resistance. The next one is charge is current times time. And then finally, the third electrical triangle that I use is work done is voltage times charge. And just remember that the units of charge are coulombs, so at the end of a question write a capital C, and they're really fussy about how you write the units to make sure it's a capital C rather than a lowercase c in order to get the mark. And remember, I just said that resistance is measured in ohms, and the sign for an ohm is like this, which I've drawn really badly. Anyway, let's look at the question then. Calculate how much charge the battery can provide before it needs recharging. So we're looking for a triangle that has Q in it. So there's 2 of those. And what else have I been told? Well, I've got the current because I've been told 5 amps. And I've been given the time, which is 20 minutes. So what I'm going to use is the QIT triangle. So I'm going to write out, because it's always good practice to do this, Q equals I times T. I is 5. Okay, T is 20 minutes, but remember that's not very scientific, so we're going to convert that into seconds by doing 20 times 60. And the answer here is 6,000. And like I just said, the units of charge are coulombs, so I'm going to write a capital C here. B, each coulomb of charge from the battery can carry 3 joules of energy. Calculate how much work the battery can do before it needs recharging. Okay, so for part B, you're going to use the formula W equals V times Q. Okay, V has been given as 4, and Q is something that I just worked out, which is 6,000. So what's 4 times 6,000? Well, it is 24,000. And work done is measured in joules. So there's the answer right there. Okay, let's look at another type of question. Okay, so I've drawn a horrendous circuit here, but hopefully it will still manage to help you at least some way. So this is an example of the sort of thing you could get in the exam. We can see that we have a series circuit with a battery made up of 3 cells, an ammeter with a reading of 0.5 amps and 3 regular resistance in series. We've been given 2 of their resistances, we don't know the third one, and a voltmeter has been added in parallel around resistance number 2. So calculate the total potential difference across the battery. Okay, so all you have to do here, because remember potential difference is the same as voltage, is add up those 3 readings, so that's 2 plus 2 plus 2, which is 6 volts. Nice and straightforward. Okay, work out the total resistance. So it'd be tempting here to try and add up all the resistances of the individual resistors. You can't do that because you don't know the resistance of resistor 3. So we're going to have to do this a different way, and we're going to use this equation triangle. So resistance is V divided by I. The V is 6, which I just worked out. I is 0.5. given by the ammeter, and therefore the answer is 12, and the units are ohms. Okay, finally calculate the resistance of R3. So if we know that the total resistance is 12 ohms, but we've been given R1 and R2, that's 6 ohms, that tells us the difference between those two values will be R3's value. So 12 take 6 is obviously 6, and that is 6 ohms. 3. The photograph shows an electrical appliance called a toaster. The toaster has a power of 1800 watts when operating at a voltage of 230 volts. State the equation linking power, current and voltage. So I'm going to put my formula triangle nice and out of the way over here. It's PIV, so P at the top, current and voltage in the bottom. So what is the equation? It is power equals current times voltage. Part 2, show that the current in the toaster is about 8 amps. So current equals power divided by voltage. I always write out the equation I'm using. We know that power is 1800, dividing it by 230 to give 7.83 to 3 sig fig, which is approximately 8 amps. Which fuse rating would be suitable for the toaster? Remember, the fuse rating needs to be slightly higher than that calculated current, and so it's not ideal because 13 is a lot higher, but you can't say 1, 3 or 7. You can't say 7 because it's lower, which means it would constantly have melted when the toaster was in use, which is why D is the correct answer here. B. The toaster uses mains electricity. Mains electricity provides alternating current. Describe the difference between alternating current and direct current. So learn these definitions off by heart. An alternating current is one where the current continuously changes direction, whereas a direct current is one where the current flows in one direction only. The photograph shows an electric heater. The power of the heater is 2000 watts. The heater is connected to a 230 volts main supply. State the equation linking power, current and voltage, and I can remember that is PIV. So therefore power equals current times voltage. Calculate the current in the heater, so rearrange so that current is power divided by voltage. Power is 2000 watts, divide that by 230 volts, and you get an answer which is 8.7 amps. Which of these fuses should be used with the heater? So you're looking for one which is higher and not too high compared with the current you've calculated, and that will have to therefore be 13 amps D because it's the only current higher than the one we've calculated. The two heating elements can be connected in series or parallel. Describe an advantage of each method. So with parallel, the obvious advantage is that you have independent control, so you can turn on and off the heating elements independent of each other, so you could just have one on or both on at the same time. The series one is a bit more of a state the obvious. Here you can use a single switch only to control both heating elements. Some electrical appliances are fitted with an earth wire. Describe how an earth wire acts as a safety feature, and that is worth 4 marks. So state that first of all the earth wire is connected to the metal casing, and that if the casing becomes live, the earth wire provides a low resistance path to obviously the earth. And then you can talk about the use of a fuse which is attached to the earth wire, so that increase in current will cause the fuse to melt, breaking the circuit, which cuts off the supply. Explain why this heater should be fitted with an earth wire, and the obvious thing here is because it has a metal casing, and remember metals are good conductors of electricity.
Right, so the topic of static electricity, there's actually not too much to go into with this. Just remember, when you're thinking about static electricity, it's all to do with electrons being transferred from one place to another. So, for example, a polythene rod, which is rubbed with a cloth, will become charged. Why? Because electrons will transfer themselves from the polythene cloth to the rod, so it will become negatively charged. That therefore means it attracts positively charged items, because remember, opposites attract. The questions always go the same, and they'll talk about why does it become charged, and literally the 2 marks you need to specify are, it's the transfer of electrons using friction. And if you actually look at past exam questions, you'll see what I'm talking about. That is so often the answer I can't even explain. Why does a balloon stick to a wall? Well, you've charged it using friction. The balloon has become negatively charged due to the transfer of electrons, and then it sticks to the wall because it repels those electrons away from the wall, meaning that it can stick to the positive charges. I'm trying to think of other questions, so things like, why do your hairs stand on end when you touch a Van de Graaff generator? That's because all your hairs become negatively charged, they therefore repel, so they stand up on end. Why can't you become charged on a metal slide when you slide down it? Well, that's because metal is a good conductor. So often they'll ask you about metals, things not becoming charged. You just need to say that it's a good conductor so the electrons can freely flow. They like asking you about the uses of static electricity, so something like spraying a bike frame. The way that this works is you give the bike frame a positive charge. You can give the paint all a negative charge, which means the paint repels itself and turns into a fine mist. Then it's attracted to the positive bike frame. One of the advantages of this is, first of all, you get an amazing finish because you get paint in all those hard to reach places. Secondly, you don't waste paint. They may ask you about the inkjet printer, not that I've ever seen a question on that, and in this instance the ink is given a charge. It falls between two deflecting plates, and then using electrostatic forces the two plates direct the ink onto the correct places on the paper, and that's how an inkjet printer works. I've never seen a question on that. I wouldn't sweat it if I were you. They may also ask you about a photocopier. Again, I'm yet to see a question. So with a photocopier, what you find is there's a rotating drum which is given a charge, and then an image of the piece of paper you want to copy is projected onto that charged drum. Now the charge drains away everywhere where the ink isn't present, and that means that when you add toner, which is a black ink, it will stick to the charged areas, which is the actual copy that you want. The rest of that toner that isn't needed is removed, and then the paper is rolled between the drum and it's nice and hot, which causes the ink to stick to the paper, and before you know it, a copy of your original paper is formed. One further use of static electricity is an electrostatic precipitator, and that's what they use in factories which produce a lot of polluting smoke full of soot and dust particles. So what happens is the smoke rises through this chimney, it's given a charge, and then there are some plates that sit at the top of the chimney that the smoke and everything has to pass through, and it's given the opposite charge, meaning that all the soot and dust particles stick to the plate, allowing just the clean air to basically escape through the top of the chimney. Then they knock those plates together occasionally, causing all that dust and sediment to fall down so it can be removed and safely disposed of. They may well ask you, however, about the dangers of static electricity. So that's things like a plane becomes charged when it's flying because of friction between the clouds and the plane. So when it lands and they bring a fuel tanker nice and close in order to refill the plane, you can imagine that a spark could go from the plane to the fuel tanker and cause a massive explosion. So that's a big no-no. So what happens in this instance is the plane is given an earthing strip which is made out of metal, because then that can conduct the excess charge away from the plane to Earth, meaning that there's no risk. Remember that lightning is an example of excess charge draining from the clouds to ground, and that's a good way of adding nitrates to the soil, which is a biology topic to do with the nitrogen cycle. And it's not really a danger, but things like TV screens and computer screens end up being covered in dust because they become charged and they attract little uncharged particles of dust, meaning that the dust covers the computer. So the wave topic, let's try and cover as much of this as possible. There are two types of wave you need to know about: transverse and longitudinal waves. Learn the perfect definition for both. Transverse waves, vibrations occur perpendicular to the direction in which the wave is travelling. Key examples here are water waves, light waves, and any member of the EM spectrum, infrared radiation, ultraviolet, X-rays, etc. Longitudinal waves, vibrations this time occur parallel to the direction in which the wave is travelling. Your key example here is a sound wave. Be prepared to draw a longitudinal wave and notice that there are periods of rarefaction and compression, so it's like a slinky. Where it comes close together, that's compression. Where it moves further apart, that's a rarefaction. Now the wave equation states that wave speed equals wave frequency times wavelength. Wave speed measured in meters per second, frequency measured in hertz, and wavelength measured in meters. What is the frequency of the wave? Well, it's the number of waves per second. If you're labeling the wave, be prepared to draw the amplitude, which is from either the middle line to the top of the wave or to the bottom of the wave. It's not from top to bottom, that's 2 times the amplitude. The wavelength is the distance between 2 peaks or 2 troughs. The time period of a wave is the time taken to produce one wave, and it's given by the equation frequency equals 1 over time period. So let's talk about reflection. That's all to do with waves bouncing. So remember, the key thing here is to know the difference between the angle of incidence and the angle of reflection. So the wave coming in and hitting the substance is the incident ray. It bounces off, and what you find is the angle at which it bounces off, so the angle of reflection will equal the incident angle. Don't forget to label your normal line, which is a line, it's like an imaginary line drawn at 90 degrees to the boundary surface. Refraction is all about a wave changing direction when it enters a new medium, and that's due to it either slowing down or speeding up, so it's due to a change in wave speed. What you find here is that if you have a light wave entering a glass block, it will slow down and it will bend towards the normal. On exiting the block, it will speed up again and bend away from the normal, so be prepared to draw that. They'll ask you to draw it for IGCSE, Edexcel in lots of different shapes, so do try and practice that before the exam. And also be aware of what happens when water waves move from a different depth. So when they go from deep water, you find that they're travelling really quickly and that the waves are very far apart from each other. As they enter shallower water, they slow down and the waves become closer together, and you'll actually see the wave front getting closer together. If you're struggling to remember that, just remember cars on a road. They'll be further apart when they're travelling nice and quickly, and then when you're stuck in a traffic jam and they're travelling slowly, they're basically on top of each other. Now, an image that can be produced on a screen is known as a real image. One which cannot be produced on a screen is known as a virtual image. You need to know the properties of an image inside a plane mirror. Now, remember that clearly the image is going to be the same size as the original object. It's going to be laterally inverted, which means your left and right sides will have swapped over in the mirror. Go check in a mirror if you don't really understand what I'm saying. It's going to be the same colour and it's going to be the same distance behind the mirror as you're standing in front of it. Now, the equation for calculating the refractive index is n equals sine I over sine r, which you'll have to learn. Now, sine I, so remember I is the incident angle, so you just need to pop that into your calculator with the sine in front of it. And sine r, that's the angle of refraction, so again, pop it into your calculator, but first of all pressing the sine button. Now, the critical angle is something they like asking you about, and it's all to do with the angle of incidence. So every type of medium, every type of substance has its own critical angle. Now, if the angle of incidence is less than the critical angle, you get both refraction and reflection taking place. If the angle of incidence is the same as the critical angle, you get a refraction which occurs along the boundary. If the angle of incidence is greater than the critical angle, you get what's called total internal reflection. So you don't get any refraction, all the light is totally internally reflected, and they make use of this in optical fibres. Now, to calculate the critical angle, you simply need to do sine c equals 1 over n, making sure you inverse sine on your calculator to get the correct value for c. Dispersion is all to do with light splitting up and spreading out. So if you get white light, remember it's made up of lots of different colours. If you shine it into a prism, it will split into those colours. Remember the order of the rainbow, and that will help you with knowing what colours the light splits into. So Richard of York gave battle in vain: red, orange, yellow, green, blue, indigo, violet. Now, red is refracted the least because it slows down the least. Violet is refracted the most because it was travelling the fastest and therefore slows down the most. What is an echo? Well, it's a reflected sound wave. Remember, they use echo sounding for working out the depth of the ocean, so they'll send down some sound waves. They'll record the time it takes for the sound wave to be transmitted and then be received again by the transmitter. You use the equation speed equals distance over time, so you know the speed of the sound wave. You've recorded the time, just make sure you halve the time, because obviously if you use the full time, then that's the time it took for the wave to hit the bottom and come back up, whereas the distance is only from the transmitter to the bottom, which is why you have to halve the time. What is ultrasound? Well, ultrasound is a longitudinal sound wave which is above the range of human hearing, so it's above 20,000 Hertz. Try and be really detailed with your answers there. Infrasound is sound which is too low for the human ear to hear, so it's below 20 Hertz. The last thing to do with sound waves is remember that pitch relates to the frequency of the sound wave. So the number of waves per second, the higher that number, the higher the pitch, so the squeakier the sound, like hi. Whereas amplitude, so that's the height of the wave, is all to do with the loudness of the sound. So the higher the amplitude, the louder the sound. So if we take my rubbish finger here, if I do that, can you see it has a very low amplitude, because it's very short, so that means it's a quiet sound, but because the frequency is very high, it has a high pitch, so it's a very squeaky sound. Whereas if I were to do this, we've got a much larger amplitude, so a loud sound, but because the waves are so infrequent, it's a very low sound.
5. A student uses a rectangular glass block to determine the refractive index of glass. The diagram shows a ray of red light in air as it enters the glass block at P. The normal at P is shown as a dotted line, which, as we would expect, is perpendicular. Complete the diagram by drawing the ray that continues inside the block. labelling the angle of incidence and the angle of refraction, and drawing the ray that leaves the block. So use your ruler here and a pencil. So remember, as it enters the block, it enters a more dense medium, so it bends towards the normal, which is why I'm doing it here. We need to draw a second normal line down here, try and draw that more straight than I have. And then remember, as the ray leaves, it is again parallel to that ray that came in, which is why I'm doing it at this angle. Now we must label the angle of incidence and the angle of refraction. So the angle of incidence is between the normal and the incident ray. The angle of refraction, it's going to be hard to show that, that's in there. And that's between the normal and the ray that has been refracted. The student measures values for the angle of incidence I and the angle of refraction R. So I is given as 60 degrees, R is given as 34 degrees. So we need to complete the table by inserting values for sine I and sine R. So that's quite straightforward. Just put into your calculator sine 60. And when you've done that, that is 0.87 to 2 decimal places. Put into your calculator sine 34, and that is 0.56 to 2 decimal places. State the equation linking refractive index, angle of incidence, and angle of refraction. So remember, refractive index is given by n. So it's n equals sine I over sine R. So in terms of calculating refractive index, sine I is 0.87, sine R is 0.56. And when you put that into your calculator, you get a value which is 1.6 to 2 significant figures. How should the student continue the investigation to obtain a more accurate value for the refractive index of glass? So that's worth 3 marks to make 3 separate points. So the most obvious point to make is to increase the reliability. You want to repeat and calculate an average. You want to vary the angle of incidence more, so you could do 50 degrees, 70 degrees, 80 degrees. And then next you could draw a graph plotting sine I against sine R, and remember that the gradient will give you the refractive index. 2. A microphone is connected to an oscilloscope to display a sound wave. The diagram shows the trace on the oscilloscope screen. The oscilloscope settings are: in the y direction 1 square is 1 volts, and in the x direction 1 square is 0.001 seconds. So let's make a few annotations. So that must mean that up to there is 2 volts, and this is 0.01 seconds, which means the entire wave cycle is 0.002 seconds. So how many periods are shown on the trace? And remember, the period is the time for one wave, so that's a complete wave. So there's the first wave, and you can see that repeats 3 times, which is why the answer here is 3. And what is the frequency of the sound wave? So frequency is given by f, which is 1 over the time period. So we simply do 1 divided by 0.002, which gives us a value of 500, and they've already given us the units, which is in hertz. On the grid below, sketch the trace of a sound wave with a smaller amplitude and a higher frequency than the wave shown by the dotted line. So a smaller amplitude means that it will be quieter, so our wave needs to be less high, so it needs to be much lower. High frequency means that the waves need to get closer together, so I'm going to draw it like this. And try and keep it nice and even. So I'm only going up one wave and down one wave, but because they're closer together, I've definitely drawn a higher frequency. The fact that they're lower means that it's a smaller amplitude.
The electromagnetic spectrum now, which is a little sub-topic of the waves topic. I do like this topic. Remember that it is a family of waves, and they vary just in terms of their frequency and their wavelength. So let's go through those waves first of all. So starting with the longest wavelength wave, so waves which look more like this. So they have long wavelengths, because remember the wavelength is the distance between 2 peaks or 2 troughs, as opposed to having short wavelengths, whereby the wavelength is this big as opposed to this big. So we're starting from the longest wavelength, that is radio waves. Then we have microwaves, infrared radiation, visible light, ultraviolet, X-rays and gamma rays, and I'll provide a link below to this video, which I love. One of my tutees told me about it a couple of years ago, and I think it's sung by some South Korean guys. If you start playing it at 30 seconds, listen to the chorus through 3 times and you'll have the order nailed in your head. Otherwise, I'm sure there are lots of mnemonics that people can remember, and comment below if you know of a good one. In terms of frequency, clearly gamma rays will have the highest frequency, because because there's more waves per second with gamma rays because they're much closer together, whereas microwaves and radio waves will have a much lower frequency because their waves are much further apart. The key point to notice with this topic is the various uses of all of these. So we'll start with radio waves. Remember, these are used in communication. Microwaves are also used in communication, so satellite communication. They're also obviously used in cooking food. Most of us have microwaves in our kitchen. Then we have infrared radiation, and that is also used in communication, and in this case we're talking about remote controls, so communicating between the remote control that you're pointing at the TV, for example. So infrared radiation is being given off there. Remember, we met infrared radiation when we were talking about the heat topic, so conduction, convection, radiation, because infrared radiation is simply heat being given off from objects, and therefore infrared radiation is the type of radiation used in ovens, because obviously they get hot to cook our food and they are giving off infrared radiation. Visible light, as well as the usual uses, so the fact that we can see stuff with them, it's also used in optical fibres and photography. Now we're getting down to the other end of the spectrum, so where the waves start getting much closer together. The next wave we're going to be looking at is ultraviolet, so UV. Remember, these are rays that come from the sun. They have various uses such as tanning beds, so sunbeds that will have UV rays being emitted, but also you can use it to check whether banknotes have been forged or not. So you hold it up to the UV light and you can tell if they're authentic. Then we're looking at X-rays. Obviously they're used in medicine to create images of the human body. And lastly, gamma rays. Gamma rays are used to sterilize surgical equipment because they're such high energy. They kill things effectively, so that could be killing bacteria on surgical equipment, it could be killing cancer cells. So used appropriately, they're very useful. If they're used inappropriately, they can actually cause cancer, so that's worth noticing. The way they'll ask the questions is it will say stuff like, microwaves are used in communication. Name 2 other rays also used in communication. You could have said infrared radiation, you could have said radio waves, or visible. So be aware here. What dangers are associated with infrared radiation? Well, because it's effectively heat, if it gets too hot, it can cause skin burns if you touch it. Dangers associated with ultraviolet, that will be skin cancer, because again, if used inappropriately, that can cause cancer, as well as the rays from the sun. If we're exposed to them for too long, it can cause cancer. How can we reduce danger from exposure to ultraviolet? Well, wearing sun cream, wearing sunglasses to protect our eyes, limiting our exposure time, covering up wearing clothes. To protect ourselves from X-rays, we need to limit our exposure time, hide behind LED screens, wear protective clothing, and the same is true of gamma rays. You really don't want to be exposed to these rays for too long. They could ask you what all these rays have in common, and that is that they are all transverse waves. So in all cases, vibrations occur perpendicular to the direction which the wave is travelling. Remember, that's your perfect definition of a transverse wave. They clearly all transfer energy. They may all be reflected, refracted and diffracted, so they can all bounce off objects. They can all change direction if they go through a different medium. And lastly, they travel at the same speed, which is 300 million meters per second. One thing they have added to the specification is the difference between X-rays and gamma rays. So remember, X-rays are made when high-speed electrons are stopped, whereas gamma rays are emitted from unstable nuclei, which we'll look at more closely in the radioactivity topic. In terms of their properties, remember that gamma is more penetrative, goes further, travels further, and gamma has the shorter wavelength because it has a higher frequency.
The table shows the main sections of the EM spectrum. So we've got gamma rays, X-rays, ultraviolet, visible, infrared, microwaves and radio waves. State 2 sections of the spectrum that are used for communications. So you're looking for the long wavelength end, which is radio waves, microwaves or infrared or visible. Any 2 picked from those 4 will be suitable. State 2 sections of the spectrum that are used for cooking, clearly microwaves. Most people own a microwave. Secondly, it's infrared, because remember, infrared is just generally heat. So an oven uses infrared radiation. The arrow below the table shows the direction of, and don't look at the answers, try and work it out and then spot the answer in the list below. So it's pointing towards the radio wave end, which means it's waves with increasing wavelength. So have a look down and it is D. The radio station broadcasts at a frequency of 200 kilohertz. The wavelength of the radio waves is 1500 meters. State the equation linking wave speed, frequency, and wavelength. So wave speed is given by v, frequency is f, lambda is wavelength. So calculate the speed. Now make sure you convert those units. So kilohertz needs to be in hertz, so times by 1000. Then we have our wavelength, which is fine because it's in meters. And when you've done that, you've got an answer which is 300 million meters per second. Don't forget the unit there. Okay, new for this specification is the types of energy. They've kind of changed the naming system. So some have stayed the same and some are new. So we're going to go through each of them in turn, talking about what they mean and some examples. So starting with chemical energy, this is to do with energy stores and it's associated with chemical bonds. And really your examples here are things like food. Remember, food is a storage of energy. The same is true for batteries. Kinetic energy, this is to do with moving an object. So anything that has movement has kinetic energy. So a man running down the road, a bus being driven along the street, they both have kinetic energy. Gravitational energy, as the name suggests, is energy associated with an object gaining height. So anything that has been lifted will gain gravitational energy. For example, a chairlift, a ski resort, an aeroplane. These all have gravitational energy, an apple being picked up, for example. Next up, elastic energy. This is the energy stored when an object is stretched, squashed or twisted. Rubber bands are the obvious place here. Catapults, balloons that have been inflated. Anything that you distort and then pings back to its original shape will contain elastic energy. Nuclear energy will become very important when we look at nuclear fission, because this is the energy associated with those reactions. So remember the fuel, uranium-235, which you do need to know, that is a huge store of nuclear fuel and therefore nuclear energy. Thermal energy, as the name suggests, is to do with heat. Anything that has gone hotter has gained thermal energy, so a hot cup of tea, for example. Magnetic energy is new for you guys, and this is the energy stored when like poles are pushed closer together or when unlike poles are pulled further apart. So like poles, remember, is two south poles being pushed together. Unlike poles would be the north and south pole. So just name any magnets here. So just a simple bar magnet, a fridge magnet that you put on the fridge door. These would all count as magnetic energy stores. And lastly, electrostatic. That's the energy stored when like charges are moved closer together or when unlike charges are pulled further apart. So very similar to the magnetic energy. And your example here is hard, but it's things like clouds. Remember when there are lightning storms? There's a huge build-up of static charge. Van de Graaff generator is the same place. Wherever you build up static charge, you will have electrostatic energy. The diagram shows some electrical appliances. Which appliance is designed to transfer electrical energy to thermal energy? So we're putting in electricity, we're getting heat out of it. It is clearly the kettle, B. Which appliance is designed to transfer electrical energy to kinetic energy? So again, we're putting in electricity, we're getting movement energy out, which would be the food mixer, A. In all appliances, energy is conserved. What is meant by the phrase energy is conserved? And that is that energy cannot be created or destroyed. It is simply converted from one form into another. The lamp has an efficiency of 20%. Explain what this means. And that means that 20% of the energy input has been transferred usefully. So in the case of a food mixer, 20% of the electrical energy in will have been converted to kinetic energy. Or you could have argued that 80% of the energy input has been wasted. Draw a labeled Sankey diagram for the lamp. Okay, so Sankey diagrams always look like this. Now you do find that a lot of it is wasted, so that's why the wasted energy arrow down here will be much broader than the useful energy. And now let's label all of them. So the lamp coming into that will be electrical energy. The useful energy out will obviously be light energy. And then there'll be wasted energy in the form of heat. Because do notice that lamps get pretty hot. Because we haven't been given any numbers, you can't add any numbers, so don't worry about that. We now need to look at efficiency. So using this example, a filament bulb was supplied with 80 joules of energy. 10 joules of energy was output as light, the rest was wasted. Calculate the efficiency of the light bulb. You need this equation. So efficiency equals useful energy out over divided by total energy in and I like to make it a percentage, so times by 100, but that's not altogether necessary. So useful energy out, we know, was the light, so that's 10. Total energy input was 80. Times it by 100, so you can pop that into your calculator or just cancel it down like I've just done. So the efficiency is 12.5%. A hamster of mass 40 grams runs up a 2-metre curtain in 5 seconds. Calculate its power. So we have mass, which I'm going to immediately convert into kilograms to make sure I don't make any errors. So that becomes 0.04 kilograms. We have distance, which is 2 meters. We have time, and we're looking for power. Now, there isn't a direct equation that links these components. Now, this question is actually more complicated than it looks because you need quite a few equations, as there's no equation which directly links mass, distance, time, and power. First equation we need is weight equals mass times gravity. The next one we need is a formula triangle, which is work done equals force times distance. And the last one contains power, which after all is what we're after, which is work done is power times time. What is the common factor linking the two formula triangles? Well, it is work done. So we need to calculate work done first of all, which is force times distance. Unfortunately, we don't have the force, so we're going to have to work that out. And this relies on you remembering that force and weight have the same unit. So if we work out weight, then we can work out the force. So we need this equation first of all, which is weight is mass times gravity. I've already told you that the mass is 0.04. Gravity on Earth is approximately 10. So therefore, the weight is 0.4 newtons. Now we're going to calculate work done using the equation force times distance. Force and weight have the same unit, which is why I can substitute in 0.4 as the force. Distance is 2 as given by the question, so the work done is 0.8 joules. And then finally we can work out power by doing work done over time. Look how I've laid out my answer with all my equal signs lined up, with all my working out shown. So the work done we know is 0.8. I'm only writing it here because I'm running out of space. Divided by time, which is 5. So that becomes 0.16. Don't forget your units for power, which is watts. Right, I'm going to go through some miscellaneous calculations to show how you should be approaching questions if you're not quite sure which equation to use. So my first piece of advice is the moment they tell you to start during your exam, turn over to a blank page and start scribbling out all your formula triangles. So you're pretty much making yourself your own personal formula sheet. Even though that will probably take you about a minute, it will be totally worthwhile because it means when you get to a particular calculation, of which there are many in the physics exam, you don't need to be scrambling around in your brain for the correct one. You just refer to your formula sheet and it should literally just be sitting there waiting for you. So let's have a look at what we have here though. So a student pushes a trolley of weight 150 newtons up a slope of length 20 meters. The slope is 1.2 meters high. Calculate the GPE, so that's the gravitational potential energy of the trolley, and calculate the work done by the student. So what do we have here? Let's identify. Look at the unit. It's a newton, which means it's both weight and force. We know the slope length is 20 meters and we know that it is 1.2 meters high. So gravitational potential energy is given by mass times gravitational field strength times height. We see an immediate issue, which is that we don't have the mass of the object, we only have its weight. So we need to do a preliminary calculation using this formula triangle, which is weight equals mass times gravity. We're looking for mass, so that's going to be weight divided by gravity. Now the weight we've been told is 150 newtons. Gravity on Earth is approximately 10. You could put 9.8, but I'm going to write 10. And therefore you're going to write the mass as being 15 kilograms. Now we're ready to use the original equation. So mass is 15, gravity I've just said is 10. The height, it says that the slope is 1.2 meters high, hence 1.2 is substituted in here. So once I've substituted that in, I get a value which is 180. It's an energy value, so it needs to be in joules.
So I've rubbed the rest out so we've got more space. So in B, we're calculating the work done by the student if she pushed the trolley with a force of 11 newtons. So we have work done, we have force. So the formula triangle we need this time is work done equals force times distance. So we're looking for work done. Let's write out the equation. Equals force times distance. The force we know is 11 newtons. The distance, look higher up in the question, she pushed it up a slope of length 20 meters. So that's why we substitute in 20 here. Pop it into the calculator and you know that it is 220. Work done, remember, has the same units as energy, which is why I'm putting 220 joules. Next equation I'm interested in is kinetic energy, which is half of mass times velocity squared. I prefer not to put this into a triangle. I think it's easier if you keep it exactly as it's written, and I'll show you how to calculate the different parts so you can actually see that it can be rearranged easily. In this first question, we're being asked to calculate the kinetic energy of a tennis ball travelling at 46 meters per second with a mass of 500 grams. So as always, write out our equation, which is Ke is half mv squared. Be careful with your units, because 500 grams isn't in kilograms, so I'm going to put that into kilograms. So remember, 500 grams is 0.5 kilograms. So start substituting in your values. So it's half times 0.5 times 46 squared. So start to simplify. So half of 0.5 is obviously 0.25. 46 times 46, or 46 squared, is 2116. Times that by 0.25, and that gives us a value which is 529. It's an energy value, so it's in joules. Calculate the velocity of a bus travelling through town with a mass of 5,040 kilograms and kinetic energy of, I'm not going to read this number out, of 527,643 joules. So writing out the equation, Ke equals half mv squared. We know the Ke this time, so I'm just going to pop that in here. I find it easier to answer these questions if I rearrange later. So half of mass, so that's half times 5040. And we're looking for velocity, so we keep that as v squared. The easiest thing now is to work out half of the mass, which is 2,520. Times that by v squared. Now we need to get v squared by itself, so the way in which we do that is divide both sides by 2520. So I'm going to do 527,643 divided by 2,520, which gives me a value of 209.382 ... equals v squared, and then we just need to square root to make sure we just get a value for v. So v equals 14.469. Notice I haven't rounded too early. I'm now going to round to 3 sig fig, so it becomes 14.5, and it's a velocity, which means the unit's meters per second.
So the meaty topic of conduction, convection, radiation, this is all to do with thermal energy transfer, so things heating up, things cooling down, starting with conduction. Now I'm sure you're aware that metals are good conductors. The reason being is due to their delocalized electrons, or you can say they're free electrons, but delocalized sounds a bit fancier. Remember the structure of a metal, you'll need to know this for both chemistry and the electricity topic of physics. So to be honest, it's worth learning. So remember that a metal is made up of positive ions surrounded by a sea of delocalized electrons. So what happens in the process of conduction is that when heat is applied, the positive metal ions start vibrating and they gain kinetic energy. What you find then is that the kinetic energy is transferred from the hot parts of the metal to the cooler parts by the presence of these delocalized electrons. So as the electrons move through the metal, they carry the thermal energy with them, vibrating the positive ions more. And before long, you can see how an entire metal object becomes hot. Now, the opposite of a good conductor is an insulator. And these are clearly going to be poor conductors. So to point out things which are poor conductors, first of all, plastic and wood. Why? Because they have no delocalized electrons, and that is the key point here. Air is also a poor conductor. It is a good insulator, and not just because it doesn't have any delocalized electrons, but clearly it's air, so the particles are going to be extremely far apart. So the chance of them vibrating and colliding with other particles to pass on their kinetic energy is going to be very slim, hence why air is a good insulator. So touching on some exam style questions, so polystyrene, why is it a poor conductor? And that's because it contains little air spaces, and air is a good insulator because it has no delocalized electrons and the particles are very far apart. So you want to link every single object you're given with whether it's a poor conductor or insulator. Next up, for example, a duvet. How does a duvet keep you warm? It's full of feathers or synthetic material that looks a bit like cotton wool. And the point is, again, that it traps air. Air is a good insulator. It's a poor conductor. So less heat transfer will take place, meaning that you stay warmer. So what have we learned? We have learned that metal is a good conductor. Air, wood and plastic are poor conductors. And that notice that solids will be better conductors than gases. Now, convection is a very different type of heat energy transfer. It only occurs in liquids and gases. You cannot get convection in a solid. It literally makes no sense whatsoever. And the key example we always use is a radiator in a house. Now, my wonderful drawing comes out. So, here's our rubbish radiator, and it's nice and hot because it's got hot water flowing through it. And what happens is that heat causes particles of air above the radiator here to gain kinetic energy. Now, because they've gained kinetic energy, the air expands, which means that the particles occupy more space. Now, because they're occupying more space, it means that they become less dense, so they rise up to here. As they rise, they become cooler. By definition, they become denser, and therefore they sink. And before you know it, a convection current has been set up whereby the process keeps repeating. And that's how a radiator in the corner of a room can actually heat up the entire room. So we've got coffee in here, and we don't want it to be getting cold too quickly. So what can we do? Well, I've already said you can put it in a polystyrene cup. Why? To prevent conduction losses. However, because the coffee is hot, can you imagine that bizarrely it will heat the air above the coffee, and it will literally set up a mini convection current above the coffee that keeps repeating itself, speeding up the process of cooling down that coffee. So what you want to do here is add a lid, and that's to prevent convection currents being set up. The other great thing about adding the lid is you add a layer of air in here, and remember, air is a good insulator. So you're preventing heat losses by both convection and conduction by adding a lid. Last up, radiation, infrared radiation, which we will have met in the electromagnetic spectrum. It is a wave, which means it is not dictated to by the state of matter. What I'm trying to say here is that it can travel in solids, liquids and gases. And that kind of automatically makes it the most difficult to try and prevent heat losses via. However, there are certain things you can do, and that's all to do with the colour of objects. So do try to remember that white shiny surfaces reflect infrared radiation, which is why in very hot countries like certain parts of Spain, you might see the houses are white. Same is true for Greece, and that's because the white colour reflects infrared radiation. Anyone with dark hair, black hair, you'll notice that your head gets really hot in the sun. Why? Because black matte objects are very good absorbers of infrared radiation. And notice that the hotter the object, or the greater the difference between the object and the surrounding temperature, the greater the rate at which heat is lost. Putting this more into context, so looking at a thermos flask, am I even going to try and draw this? Oh God. Okay, so that's appallingly drawn, but I can still point out a few things. So, first of all, the most obvious thing here to point out is that it has a vacuum. Now remember that a vacuum is a space with no particles, and we know that both conduction and convection require particles in order to occur, so we say that there is no conduction or convection that can occur within this vacuum. And as always, I'm linking the property with which type of heat transfer it prevents. There are silvered surfaces which line the bottle or line the flask. And the point of that is that it reflects infrared radiation back at the contents of the flask, keeping it hot or keeping it cold. The lid prevents convection currents, which I've already touched upon. And you can say that the whole thing is made out of plastic because plastic is a good insulator. And that's the way you get these answers nice and scientific, is by pointing out the various parts of it and what it stops. So looking at heat transfers within a home, how can we stop all our heat escaping? So first of all, in the loft, you can have loft insulation, which contains lots of air spaces. Air is a good insulator, preventing conduction heat losses. You could talk about the cavity walls. So cavity meaning a hole, like a cavity in your teeth. So there's holes within the walls which contain air, again because air is a good insulator. Do notice though that convection currents can still be set up in air, which is why you often find there's also foam, because that solid foam stops the convection currents being set up. You could talk about the radiators now having a silvered surface, and that's to reflect infrared radiation back at the room. And lastly, double glazing. Remember, that's when you have two window panes which trap air between them, helping to prevent conduction. Question 9. The diagram shows how air moves near the coast on a warm day. Explain why air moves. Explain why air moves as shown on the diagram. Hopefully the fact that there are arrows and we're talking about a gas, which is air, and heat, hopefully that's screaming convection at you. So again, this is a perfect answer. You need to rote learn your convection answer. So first of all, state that energy is transferred from the sun, which heats the land. This means that air above the warm land becomes warmer, so the particles gain kinetic energy, and effectively the air expands and becomes less dense. This means that that heated air rises, and therefore there's a space, so cooler, denser air falls in order to replace that warm air, and you've therefore created a convection current which repeats. So this is a convection current answer which you need to just learn off by heart, although they have given you a different scenario to the usual radiator in a hot room, so try and make it applicable to the question. So let's start by looking at the warm land. Initially, the warm land heats the air, and that means that the air has gained kinetic energy, so the air expands, becomes less dense, and rises. So as that warm air moves over the sea, it becomes cooler and therefore denser. So that cooler, denser air falls and replaces that air that was above the warm land, and then by doing so you've created a convection current which keeps repeating itself. Explain how Brownian motion provides evidence that air is made of small particles. So remember Brownian motion, our example here are pollen grains in water or smoke particles, and remember that these large particles move with random motion and they collide with smaller invisible particles, and that's the particles which we find in air.
There's always something about renewable, non-renewable energy. So non-renewable energy is things like fossil fuels, so coal, natural gas, oil. These are things which are running out. They're very good at providing us with energy, but if we carry on using them at the rate we're using them now, we're going to run out. And because they come from fossils, they are not going to be replaceable. So we're turning to renewable energy, things like solar, wind, hydroelectric, geothermal, all those sorts of things are renewable energy, and you need to be able to state the advantages and disadvantages of both. They all tend to have the same kind of disadvantages, which is that they're unreliable. So for example, if there's no wind, there'll be no wind power, no sun, no solar, no waves, no wave power. The only type of reliable energies out there are things like hydroelectric, because that's, remember, when water falls down a dam. that tends to be quite reliable unless there's been no rain. Geothermal tends to be very reliable, but remember there's only very certain places on Earth where you can harness geothermal energy. Places like Iceland, where there's a gap between the two tectonic plates. So places like in England, you won't be able to get geothermal energy. They could ask you how energy transfers occur, for example, inside a hydroelectric power station. They do like to ask you that, because remember, water gains gravitational potential energy because it's at the top of the dam. As it falls over the dam, it will gain kinetic energy transferred into electrical energy to therefore power houses. This might seem quite bitty, but I'm just literally racking my brain to think of the questions they'll ask you. They could ask you how a fossil fuel power station works. And actually any power station kind of works in the same way, which is that either if they're burning biomass or they're burning fossil fuels, what you're doing is you're heating water. That water turns into steam. The steam turns a turbine turns a generator, and a generator generates the electricity. So those are all the steps involved in generating electricity. Nuclear power is quite an interesting one because it's not technically renewable because you can't make more radioactive material. However, such tiny amounts are needed, it means that it's very unlikely to run out. So there is a huge potential for nuclear power. However, disadvantages include the fact that there's radioactive waste which needs to be stored very carefully, because if that escapes into water supplies, that could cause cancer. There are high decommissioning costs, and that means it's just very expensive taking the whole power station apart once it's been used for about 20 years or so. High startup costs obviously follow, so it's going to be expensive to make those factories in the first place. So we're looking now at the density and pressure topic. So remember, density is to do with how close together particles are. Heavy objects have high density, and that's because the particles are close together. Lighter objects are less dense, and that's due to the further apart spacing of the particles. Now the equation you need to know about is density equals mass over volume. Now I use a formula triangle as usual to remember this, and one of my tutees taught me a good way to know this is drunk men vomit. So you want D at the bottom of the triangle, M at the top, V at the bottom. So to work out density, it's mass over volume. Mass is density times volume, and volume is mass divided by density. They're quite interested in you being able to determine the density of various objects. So let's start with symmetrical objects, things that we can easily measure the volume of. So things like cubes, cuboids, brick, for example. Now what you want to do here is, obviously looking at the equation density equals mass over volume, you want to measure the object's mass using a top pound balance and get that measurement in kilograms. Then to measure the volume, we simply use a ruler. We measure the length, width and height, multiply those values together to work out the volume, substitute in your mass and volume values into the equation, and out pops the density. Now it's going to be far more difficult measuring the density of an asymmetric object, something like an ornament or a vase or a stone, and that's because you can't easily measure the length, width and height of the object, so it's very difficult to determine its volume. This time we're going to use the displacement method. The simplest way to describe this is you fill a measuring cylinder with water, you measure the volume, then you add the object to that measuring cylinder and you measure the new volume, and the difference between those two values will clearly be the volume of the object, so its volume is now sorted. Its mass is easy to determine using the top pound balance method. Substitute the values into the equation, so make sure you state the equation in your answer, that will be worth a mark, and out pops density. Now pressure. So pressure is acting all around us. Remember that pressure around atmospheric level is 100,000 pascals or 100 kPa, and that pressure increases underwater. And if anyone goes scuba diving, you'll know this. When you have to do your training, you need to be aware of the pressure around you. And the reason the pressure increases is simply because there's more water above you, the atmosphere above that, and it's all bearing down on you, hence you experience a higher pressure. At the top of mountains, you'll have less pressure, and that's simply because there's less air above you. Now, in terms of when you go up in an aeroplane, just to try and give you some context, has anyone ever noticed that you get bread rolls in those little plastic packets, or a packet of crisps, and it looks like a pillow in an aeroplane? You get super puffy, and that's because when the packet of crisps, for example, was sealed at ground level, then you have the atmospheric pressure around, so that gets sealed into the packet. And so you've got those particles colliding, creating pressure against the walls of those crisp packets. However, when you go into an airplane and you're at altitude, then what you find is the surrounding air, there's less pressure. So you find there's more pressure within the crisp packet, less pressure surrounding it, which is why it puffs out. So when we look at solids, liquids and gases, be prepared to draw their particle diagrams. Notice that solids have particles which are in very fixed arrangements, and that's because the particles vibrate around in fixed positions, they have little kinetic energy, and there are strong forces between them. Moving to liquids, you see that the particles are slightly more widely spaced apart, they're not touching quite as much, so they have intermediate forces between them, and they vibrate more, and they don't have fixed positions. Gases now, so you need your particles to be further apart. This is because they have large amounts of kinetic energy. Obviously they're not held in fixed position, and there are weak forces between the particles, and here's your summary now. Let's start naming the correct conversions between all these various states of matter. So remember, if you're going from a solid to a liquid, that is melting, like a solid ice block turns into water, melting. If you go the other way and the water turns into ice, clearly that will be freezing. If you have a liquid and it turns into a gas, that will be boiling or evaporating. And then when you have a gas and it turns back into a liquid, that is condensation. So that's what happens when you have a shower and you see it getting all misted up on the windows. Condensation is occurring here. Touching slightly more on evaporation, so how does the evaporation of a puddle or any liquid happen really? So what you find is that the particles have differing kinetic energy. Now those particles with the most amount of energy will evaporate first, and they will leave the surface of the liquid. And what will happen is it will mean that the remaining particles have lower average kinetic energy. Do notice that in a closed container, condensation and evaporation will be occurring simultaneously, which means at the same time. And you need to be able to describe what pressure is in terms of particles. So taking particles within a crisp packet or within a container or within a squirty cream container, just remember that those air particles collide with the walls of the container. No, what are you doing? Lyra? No, no claws, no claws. No claws. No claws. Should get rid of this. Please be good. Be good. She always meows when I talk to her and she knows she's being naughty. Lyra! So, those particles collide with the walls of the container, creating a small force, and that force given over a specific area is the pressure. And we know this because of the equation pressure equals force over area, so you can use the triangle FAP to help you remember that. Do be prepared to provide answers to what pressure is or how pressure is produced within a container, as that could be worth 4 marks. And do remember those particles within the container have random movement because they are air particles and they are a gas. Why does that pressure increase with increased temperature? Well, clearly increased temperature provides those particles with greater kinetic energy, which means they collide with the walls of the container both more frequently and with greater force, hence you see an increase in the pressure. So if we go the opposite way and we decrease the temperature, clearly decreasing the temperature will decrease the kinetic energy. Eventually the particles will have no kinetic energy whatsoever, and at this point we say that absolute zero has been reached. Because the particles have no kinetic energy, there is no pressure. It has a value which is minus 273 degrees Celsius, and if we're using the Kelvin cycle, which is a different scale for measuring temperature, so we are used to dealing with Celsius, however the Kelvin is also a very good system, and we say that absolute zero is 0 Kelvin. So be able to convert between the two scales, so minus 273 degrees Celsius is 0 Kelvin. So in order to convert between the two, to get from Kelvin to degrees Celsius, you want to add 273. And to get from degrees Celsius to Kelvin, you want to minus 273. So let's take an example, 20 degrees Celsius. What is that in Kelvin? It is 293 Kelvin because we've added 273.
Here I'm looking at a question, so which exerts more pressure on the ground? A tank with a weight of 80,000 newtons or a cyclist with a weight of 1,000 newton? The tank tracks have a contact area of 10 meters squared and each of the cyclist tyres have a contact area of 0.6 meters squared. So what you need to do is begin by drawing the triangle to help you sort out your formula. So it looks like this: forces at the top, then it goes area, and then it goes pressure. So I'm going to change to black. So I'm obviously looking at the pressure, so I need the form of the equation which looks like this: force over area. I'm going to start by looking at the tank. So its pressure will be its force, and obviously that will be the 80,000 newtons. Why? Because weight and force have the same units, so that is newtons, and therefore we can use them interchangeably. So that's 80,000 divided by the area, which I've been told is 10, and here's the answer, 8,000 newtons per meter squared. Now let's look at the cyclist. Okay, so the pressure will equal the force again, which is this time 1,000 newtons, divided by the area. Now don't make a mistake here. The area is 2 lots of 0.006. The reason being because obviously the cyclist has 2 tyres. So I'm going to do 0.06 times 2, which equals 1,000. Please don't let me run out of space. By 0.012. I'm going to use the calculator here. And the answer here is 833 meters squared. So, as you can see, it's obvious that the cyclist exerts more pressure because their pressure is 83,333. So make sure you write that the cyclist is the answer. Question 4. A diver works in the sea on a day when the atmospheric pressure is 101 kilopascals and the density of the seawater is 1028 kg per m cubed. The diver uses compressed air to breathe underwater. 1,700 litres of air from the atmosphere is compressed into a 12-litre gas cylinder. The compressed air quickly cools to its original temperature. Calculate the pressure of the air in the cylinder. The only reason these questions are hard is because you need to actually pull out the information in the question, but once you've done that, it's straightforward enough. So what numbers have we been given? Well, we've been given atmospheric pressure of 101 kPa, density, which is here, but I don't think we need to use that quite yet. We've been told that 1,700 litres of air is compressed into a 12-litre gas cylinder. So we can see here straight away we've got 2 volumes, we've got a pressure, and we've got another pressure. So which equation contains 2 lots of volumes and 2 lots of pressures? Well, it's this one. Correct me if I'm wrong, but I think this is given on the front of your paper, but it's quite straightforward to remember anyway. Just make sure your units are all the same and then start subbing in these numbers. So pressure 1 is going to be 101 times volume 1, which is 1,700, equals, we're looking for P2, so we'll keep that there, times 12. And then the way to work this out is work out the left-hand side first of all. So 101 times 1,700. And then divide both sides by 12. And then when you round that to 3 sig fig, you're going to get P2 equals 14300. The units will be kilopascals. State the equation linking pressure difference, depth, density, and G. So you can write this out in words. You can literally write pressure difference equals depth times density times G. Or you can write it out as symbols, which would be P equals H times, remember it's the Greek letter rho, which looks like a P, so that's why it's a bit confusing, times G. So if in doubt, I would write it out in words. Whatever you do, don't write gravity for G. They're very fussy over this. You need to write acceleration due to gravity. Calculate the increase in pressure when the diver descends from the surface to a depth of 11 meters. So what you're going to do here, I'm just going to write out the equation. So pressure equals height times density rho times G. So 11 times density, which we were given right at the beginning of the question, which is 1028 times G, which is 10, and we need to know that number. You can use 9.8 also, but 10 is easy. And then you work that out and you get an answer which is 110 kPa. Part 3, calculate the total pressure on the dive at a depth of 11 metres. Assume that the atmospheric pressure remains 101 kPa. Well, because it's worth only 1 mark, they've only given you a small gap. You shouldn't be doing any proper calculations here, so no substituting into equations. You simply need to add together your previous value to the atmospheric pressure. So that's 101 plus 110, which equals 211 kilopascals. C. As the diver breathes out, bubbles of gas are released and rise to the surface. The bubbles increase in volume as they rise. Explain this increase in volume, 2 marks. Make 2 separate points. One of the most basic arguments you can make here is that it will be warmer closer to the surface of the sea because you're closer to the sun. That would be worth 1 mark. And what that does, because remember, if it's warmer, the particles vibrate more, and therefore the pressure will increase inside the bubble, which leads to its volume increasing. Or you could give an argument to do with the fact that pressure decreases closer to the surface. Always provide an equation in this case, so that would be pressure equals height times density times g. And then you would state that the PV value is constant for a fixed mass of gas. And if that sounds weird, you can state the other pressure equation once again, which is P1 times V1 equals P2 times V2. The diagram shows some gas particles in a container. The piston can be moved in or out to change the volume of the gas. Add arrows to the diagram to show the random motion of the gas particles. Just literally show them just moving around really randomly. Just make sure you add enough arrows. They're just a gas, so it's quite straightforward. Explain how the motion of the gas particles produces the pressure inside the container. This is an answer you can rote learn. So you want to first of all talk about the fact that gas particles have random motion and that they collide with the walls of the container. Then this creates a force, and then lastly state an equation which is pressure equals force over area. And that is the easiest way in which you'll get 3 marks. I would really recommend you learn that answer off by heart. State what would happen to the pressure if you push the piston into the container without changing the temperature. Well, you've got a smaller volume, so therefore the pressure would increase. When the gas in the container is heated, the piston moves outwards. Place ticks against the 3 correct statements. The gas particles get bigger. No, that's not true. The mass of gas particles stays the same. Yeah, that makes sense. The gas particles move faster. Well, clearly, if you heat them, they're going to gain kinetic energy, so they will move faster. The average distance between the gas particles increases. Again, true, because if they're moving faster, they'll be moving away from each other, therefore increasing the distance. The temperature of the gas decreases. Well, no, the container's been heated, so that's absolute rubbish. I'm going to show you some more density questions because I've touched on this density triangle, which I told you is drunk men vomit here, but there's another equation you need to be aware of with density, which I'm going to bring up now because I found this particular example so I could talk about it. So question 6, this question is about pressure in a liquid. A teacher uses this apparatus to demonstrate pressure difference in water. The apparatus is hollow and has 3 short tubes at different depths. The teacher completely fills the apparatus with water and water comes out of all the tubes. So look, path of the water from the top of the tube. State the relationship between pressure difference, height, density and G. So I wouldn't use a triangle here, you do just need to learn this, and it is pressure difference equals height times density times G. That does not look like a G. Don't know why I can't draw that times properly. The diagram shows the path of water coming from the top tube. Complete the diagram by drawing the paths of water you would expect to see from the other tubes. Now notice that this question exists. I have a lot of people I teach that probably wouldn't even have spotted that that was a question and would have lost 2 marks immediately. So do make sure you read every single question and that you indeed attempt every question. Now I already told you that the lower down you go in water, so the further under the ocean, the same is the case here, the greater the pressure that is experienced. That means that the path of water coming out of the lowest pipe will have travelled the furthest due to that increased pressure. So we're looking at something like this. And then for the middle tube, you're looking for an intermediate path. So like that. Explain the pattern of the paths of water from the tube. So I've accidentally already alluded to this. You want to say that the water at the bottom of the tube has greater pressure and therefore the force acting on it is the greatest, meaning that it travels furthest. In another demonstrator, the teacher uses this container. The container is made of glass and each section has a different shape. The teacher pours water into the container until it reaches the level shown in the left-hand section. Complete the diagram by drawing the water levels in the other 4 sections. So this is probably quite a hard question, so just be aware that the air pressure is the same for all vases. After all, they are connected, and that means that the water level will be the same for each regardless of the shape. Make sure you actually draw within the vase. I have a habit of drawing outside of the vase, so I'm going to use in the exam a ruler to show that it is constant for each vessel. Explain why the water fills the container in the way you have shown. So we need to describe why we've drawn it at that constant level. Well, I've already said that the air pressure is the same for all, so that's worth 1 mark. We know that it's water, we know we haven't changed liquids throughout, therefore the density of the liquid will remain the same. And then look at how that equation links. So pressure difference equals height times density times g. Gravity hasn't changed, density hasn't changed, pressure hasn't changed, therefore height won't change, hence the same height for each. And lastly, you could point out that the vessels are connected.
So, magnetism. Well, we're going to start by first of all stating which metals are magnetic. That is iron, steel, cobalt and nickel, and the 2 most common examples you'll come across are obviously iron and steel. Do notice that steel is an alloy of iron, which means that it contains iron, but it also contains the element carbon. A few basics to point out, which is if you have a bar magnet or any magnet, remember that 2 north poles will repel, so if you try and push them together, they'll slide past each other. The same is true with south poles, they'll repel as well, and the opposites attract, so a north pole will attract a south pole. Looking at the difference between a soft magnetic material and a hard magnetic material now, the real difference is that a hard magnetic material maintains its magnetism. So steel, for example, is a hard magnetic material. It does not lose its magnetism easily, whereas iron loses it very easily. And to put this into context, if we use a scrap metal yard as our example here, scrap metal yards are full of big old lumps of iron which need moving around. Now you actually use a magnet to move them around, and what you do is you turn on a massive iron electromagnet and it becomes magnetized. It clamps down and picks up that metal that it's trying to move, and then when you've moved it across to the new position, you can basically cut the power source and it will lose its magnetism. You couldn't use steel in this case because you'd effectively find that all that scrap metal would remain stuck to the magnet and you'd never be able to pull it off. So what is a magnetic field line? Well, it's the space around a magnet whereby magnetism can be detected. And in terms of designing experiments whereby you can determine the shape of magnetic field lines, you have 2 options here. First of all, iron filings, and secondly, using plotting compasses. So what you do is you get a piece of paper, you sprinkle iron filings onto it, and then you place a bar magnet underneath, and you'll see that those iron filings align themselves with the magnetic field. With a plotting compass, instead, you place your bar magnet on a piece of paper, you place a plotting compass near to it, and you make a note of the direction in which the arrow on the plotting compass is pointing, and then you pick it up, put it in a new position, keep repeating that process until you've drawn the magnetic field lines. Now just remember that a solenoid is a cylindrical coil of wire. Touching now on the right hand grip rule, so this is just a way of showing the direction of magnetic field lines. So my thumb represents a wire, so in this case it's going from north to south or from up to down, and you might be asked to draw the magnetic field line directions and just follow the direction which your fingers are pointing. Be aware of a uniform magnetic field, and all you'll see here is that the magnetic field lines are evenly spaced and that they're parallel, and those are the 2 points you need to point out with a uniform magnetic field. So how can an object's magnetism be induced? So how can it become magnetic? Well, first of all, you need to start with a magnetic metal such as iron and steel, and then you can place it inside the magnetic field of a permanent magnet, and its magnetism will be created or induced. Obviously, the moment you remove that object, the iron object, from that magnetic field, it will lose its magnetism. Steel, I've already pointed out, is a hard magnetic material, so it will tend to retain its magnetism. So how is a simple electromagnet constructed? And that's simply by connecting a wire to a circuit and running a current through it. How can we increase the strength of the magnetic field of that wire carrying a current? Well, the most basic thing we can do is obviously increase the current, and we can also wrap the wire into a solenoid. So if we coil it up, that will also increase its magnetic field strength. We're now interested in increasing the magnetic field of a solenoid. Because it's already in a coil, what you can do now is add more turns of coil, or you could add an iron ore, which is just like an iron bar which you thread through the middle of the solenoid. You can also increase the current, as I've already specified. We're now looking at the motor effect, which is the part of this topic which people really aren't a fan of. But if I talk you through the overview first of all, and then we'll look a bit more closely about how it all works. So let's start by looking at what the motor effect really is. And all the motor effect is, know that a motor is a piece of wire that spins. So that's what's happening in a motor, a wire is spinning. And we're trying to work out how we can create that, and that is via the motor effect. And you might have seen a simple motor being built at school. So what you have here is you have two permanent magnets. You have a wire in between them which is coiled up, and then that is attached to an electrical circuit so it can carry a current. And the point here is that when the wire carrying the current is placed within this magnetic field of the two permanent bar magnets, you find that there's a phenomenon which we call the motor effect. And what will happen is that wire will start spinning and you have a simple motor. But that's only if you've got a coil of wire placed within the magnetic field of two permanent magnets and it needs to carry a current. And you've probably heard of Fleming's left-hand rule, and that's what I'm going to talk about now. And that's just a way of working out whether the coil moves up on one side or whether it moves down, because obviously it has to move up to begin its spin, then it moves down, moves up, it moves down. So that's what's happening with our motor. So looking at Fleming's left-hand rule, you've got to hold your thumb, forefinger and second finger at right angles to each other. Now the thumb represents the force or the motion, and that will show the direction in which one side of that coil will be moving. So taking the left-hand side, for example, in this instance, it would be moving upwards. The first finger, the first finger shows the direction of the magnetic field, and remember that the magnetic field always runs from north to south. So based on that diagram you get given in the exam or in your textbook, have a look at those two permanent bar magnets, look at the North Pole, look at the South Pole, and make sure that your first finger matches up with that. Your second finger shows the direction of the current, and on your textbook it should show an arrow showing which way the current's running, if it's running clockwise or anti-clockwise. Just make sure that that finger is lined up there. So once you've lined up your magnetic field, which is your first finger, your current, which is your second finger, you will find that your thumb either points up or it points down. And so it will ask you which direction will the coil move, and you will say upwards or you will say downwards. But just make sure you've got them all in 90-degree planes to each other. My way of remembering what finger stands for what is that the first finger is your magnetic field, first field, second it contains a C, means that it is showing you the direction of the current. So in terms of answering the 5 markers, which tend to be something like a wire is placed within the magnetic field and a force is felt. Discuss. It's worth 5 marks. So it doesn't matter how they word up these questions, the answer is always the same. You want to start by saying the wire carrying the current, so your coil, has a temporary magnetic field, and what that does is it interacts with the permanent magnetic field of the bar magnets. This creates a force causing the wire to turn, and believe it or not, this applies as well when you're talking about a loudspeaker, because anything that moves in and out in this way involving magnets will use the motor effect, even though it doesn't seem particularly obvious. So taking the speaker cone, for example, we start by saying that the wire carrying the current has a temporary magnetic field. This interacts with the permanent magnetic field of the bar magnets found in the speaker. This creates a force, and this force moves the speaker cone upwards, vibrating air particles, causing the sound that reaches your ears. So you're using the same answer here, and honestly, as long as there's a wire moving or the speaker cone moving, your answer remains the same.
The photograph shows a small electric motor. Explain why the coil starts to spin when the switch is closed. Remember, this is a magnetism question, so this is an answer which you can definitely rote learn. So what you want to say is when the switch is closed that the current flows around the circuit. This creates a temporary magnetic field around the magnet, which you can see is near the coil. It's stuck in the coil, so right here is where the magnet is. So this temporary magnetic field interacts with the permanent magnetic field of the magnet, which creates a force, and that force is what is used to turn the coil. And you can mention Fleming's left-hand rule just for an extra mark. So just how to make the coil spin in the opposite direction. The obvious thing here is to switch the direction of the current, or you could have swapped the magnets over. So just how to make the coil spin more slowly. So how do we weaken that magnetic field? Well, we can reduce the current. You could also reduce the voltage or had a weaker magnetic field, which is harder to quantify. 3a, state what is meant by the term magnetic field line, and that's a line that shows the direction of the magnetic field. The diagram shows a cross-section through a wire placed between two magnetic poles, and the wire carries electric current into the page at X. The shape of the magnetic field is shown. Add arrows to any two lines to show the direction of the magnetic field. Now remember that it runs from north to south, and we have to do that on at least two lines, so I've done two there. Draw an arrow on the diagram to show the direction of the force on the wire and label this F. So this is where Fleming's left-hand rule comes in. So remember that your thumb shows the direction of the force, your index finger shows the direction of the magnetic field, and your second finger shows the current. So make sure you're holding your left hand up here. Make sure that your second finger is pointing downwards at X. Then line it up so that your first finger is pointing north to south. And then when you've done this, you'll see that your thumb is pointing to the right. And remember, that shows the force, which is why it's in this direction. Now we need to describe the magnetic field in the region shown inside the dotted square. So if you have a look at that, you can see that first of all, the magnetic field isn't uniform because the lines are differing spaces apart. And also notice that they're flowing in the same direction, so they are parallel to each other.
Now we're going to look at electromagnetic induction, or basically how voltage or current may be induced. It's a very similar concept, we just need to look at it from a slightly different angle. So I hope you realise that with your force and your magnetic field and your current, it's a bit like a physics formula triangle, which is that if you put in magnetic field and you put in current, then you get force. So it makes sense therefore that if you put in the force, you put in the magnetic field, then you should be able to make current. And indeed, that's what electromagnetic induction is all about. If a wire is moved into a magnetic field at right angles, then you find that a voltage will be induced. And if it's connected up to a complete circuit, that's where your current comes from. Do notice that you must move the wire or the magnets, it doesn't matter which way around you do it, but you must move them at 90 degrees to each other. If they're parallel, then you won't induce your voltage. Now, in terms of working out which direction everything's going to move in, this time you use Fleming's right-hand rule. So you find again that the thumb shows the direction of the force or the motion. First finger is the magnetic field, second finger is the current, but you have to use your right hand because otherwise it won't line up properly if you use your left hand. And this is really how a simple generator works, because if you're creating current, then clearly you could make electricity from that, and all a generator is a machine which creates electricity. So how could you increase the size of that induced current? Well, clearly you could use stronger magnets, you could have a stronger magnetic field, you could move the wire more quickly, and you could wrap the wire into a coil. Looking at the use of generators in everyday life, you can use the example of a bicycle dynamo. And just to explain what this is, so some bikes, I don't know if you've ever used the Boris bikes in London or any of those bikes you can rent in other countries. I don't know if you've ever cycled them in the night time, but they have lights, and it's not because they have batteries that need replacing, it's because they contain simple dynamos, which uses your motion of pedaling the bike to actually power the lights. So we need to explain from an electromagnet point of view how that works. So as you turn your pedals, clearly the bicycle wheel turns. This turns a magnet which is located within a coil, and this magnetic field of the magnet cuts the surrounding coil, which induces a current. So within a bicycle dynamo, you find that there is indeed a simple generator. Also be aware of the roles of the relay switch and the circuit breaker and an electric doorbell. Do notice that with these sorts of questions, it's most likely they'll give you a diagram, and it's just up to you to describe what is happening. So always start with the switch when you're talking about the doorbell. So you press the switch, causing a current to flow. The current flows to the electromagnet, causing it to become magnetized, and the designs of these bells will vary a fair amount, but they're fundamentally the same. There'll be an iron rod or an iron armature which will be attracted, and because of the way it's pivoted, it means that it's attached to a bell that hits a gong, and that's how the doorbell sounds. So just make sure you look at the diagram you're given and follow those steps around, starting from the switch being pressed and you will get your marks. Do notice that a relay switch is effectively a safety device. It's used to turn on very large currents. So what you find is you press the switch to complete the circuit, and it will be attached to a different circuit which contains a much larger voltage, and it's a safety device because you don't want the person touching the switch attached to the very high voltage supply such as 1 million volts, because if there's a fault it could easily kill them, it could electrocute them. And this is seen in things like floodlights at stadiums. There can be millions of volts going through those huge lights. You don't want the person in danger, so that's where a relay switch may be used. And you can also find it in car engines. You turn your key, that will be involved in a relay switch, which will be involved in turning on the car engine. With the circuit breaker, this is a safety device used in houses. So it's when the current becomes dangerously high, you find that the electromagnet becomes magnetized, pulling away part of the circuit, meaning that the circuit is no longer complete, and therefore you cut off the supply. In electricity, you'll have met fuses. They work in a similar way. They're both safety devices. However, you will find that a circuit breaker is preferred because it responds far more quickly, and it's much easier to reset because you simply press a button. Now it's time to look at the maths element of this topic, so we need to look closely at transformers and using the various equations involved in that. Diagram 1 shows some of the apparatus used to investigate the force on a current carrying wire XY in a magnetic field. Diagram 2 shows the poles of the magnet viewed above. Draw the uniform magnetic field between the poles. Okay, this isn't as hard as it might sound. You just need to draw straight lines, so use a ruler. I'm not using a ruler because I'm using the iPad. And you need to do a minimum of 3, and then obviously the magnetic field goes from north to south, so add arrows showing that, and that is more than enough. The current carrying wire XY is at right angles to the magnetic field. The current in the wire is 10 amps. Suggest why the wire used in this investigation must be thick. Any sensible suggestion? So otherwise a large heat might cause it to melt if it was too thin, or you could say a thicker wire is used to reduce the resistance, or you could say that it doesn't, so that it doesn't sag or bend. Explain why the wire XY experiences a force when there is a current in the circuit. So have another look here. This is quite hard, but just say that the magnetic field of the wire interacts with the magnetic field of the two magnets, and you actually get a mark for just mentioning Fleming's left-hand rule. These questions are strange with electromagnets. Just kind of write down everything you know, even if you're worried about whether it actually fits the context of the question. State 2 ways in which this force may be reduced. Okay, you could reduce the current, or you could use less powerful magnets. The photographs show how an electric toothbrush fits on its charger. The charger and the toothbrush each have a coil of wire inside them. The diagram shows how the two coils are linked by a U-shaped core. This arrangement of core and coil acts as a transformer that reduces voltage. Name the type of transformer that reduces voltage. Well, that would be a step-down transformer. Explain why the core is made of a soft magnetic material such as iron. Remember, it's because iron is softly magnetizing, and therefore it loses its magnetism easily, and also you need to state the fact that the magnetic field in the core can change. State the equation linking the input primary and output secondary voltages and the turns ratio of a transformer. This is something you're just going to have to learn. So write input voltage divided by output voltage equals primary turns divided by secondary turns. Please just learn that off by heart. The transformer has 520 primary turns and 30 secondary turns. The input voltage to the transformer is 44 volts. Calculate the output voltage. So let's just substitute those numbers in. So that calculation will look like this. The input voltage is 44. We're looking at the output, so I'm going to put X here. Primary turns is 520. Secondary is 30. It's up to you what maths you want to use to do this. What I tend to do is flip the whole lot, so it becomes X over 44 equals 30 over 520. And then all you need to do is use your calculator to do 30 divided by 520 and then times it by 44 to get X by itself, and X will equal 2.5 volts.
Diagram shows parts of a transformer. The input voltage to the transformer is 230 volts, the output is 25, there are 100 turns on the secondary coil. Name the type of transformer shown in the diagram. Well, it's a step down because the output voltage is lower, so write step down there. State the equation linking input primary voltage, output secondary voltage, primary turns and secondary turns. We really need to learn all these equations. So this is what the equation is. Remember that it's input primary voltage over output, which is secondary voltage, equals number of primary turns divided by secondary turns. So now we're calculating the number of turns on the primary coil, so I'm going to be using that equation, and X is therefore NP here. And then let's substitute what we know. We know that there are 100 turns on the secondary coil. Oh my gosh, the gardeners are so noisy. And then on the output of the transformer, we've got 25 volts, so that's voltage on the secondary. And then if you scroll up, you'll see that the input voltage in the primary side is 230, and now you need to solve that for X. So just do 230 divided by 25, times it by 100, and you'll have 920 turns. B. Explain how a transformer works. In your answer, you should include the reasons for using two coils, the iron core and alternating supply. Don't stress too much if you're like, oh, I don't know how to crowbar those things into my answer. Just write what you would write normally and you'll find that they'll just fit in. So first of all, say that transformer either steps up or steps down the voltage. Say that the current in the primary coil produces a magnetic field. For the third mark, say that this current is changing, which causes a changing magnetic field in the core. You need to say that the core strengthens the magnetic field. Then state that the field lines interact with the secondary coil and that this induces a voltage in the secondary coil. If you think I said that quite fast, just rewind this video and listen again. But you do need to learn all the steps. It's a nightmare and I hate magnets too. You're not alone.
We start by looking back in history and look at the original structure of the atom so we can actually understand all our findings that we know to be true today. So originally there was the Thomson plum pudding model. Now you don't need to know too much about this, but just know that a plum pudding, this was in the 1800s by the way, so you can imagine a Christmas pudding if you don't know what a plum pudding is. I don't know what one is. So a big sphere of sponge embedded with different types of fruit, and in the case of the plum pudding, those were plums. And Thomson stated that the sponge was made out of positive charge and that those plums embedded within that sphere of sponge were the electrons. Now we know that this is false because we now know the modern day structure of the atom with its nucleus and its shells with the electrons circling, and we're going to talk about the gold foil experiment to help us understand why this new atom became the accepted model. So Rutherford fired alpha particles, and we'll talk about alpha particles soon, at gold foil. Now he found that most of them passed straight through, and this was strange because really if the atom was structured like a plum pudding, there's no way these alpha particles should have passed straight through, but because they passed straight through, it told him that the atom is largely empty space, which we know to be true. Some alpha particles were deflected, and because an alpha particle is positive, it told him that they had hit something also positive and that they had been repelled, and that made him understand that the nucleus was positively charged, which we know to be true because that's where the protons are found. Lastly, very few of the alpha particles were deflected in this way, and this told him that the nucleus was very small. So do link together what he did with what findings he found out and the conclusions he drew from those findings, and that will help you score really highly. So we now have our structure of the atom. We know that it has a nucleus containing protons and neutrons. Remember, this is also known as the nucleon number, and that's just the name given to all the particles found within the nucleus. And surrounding the nucleus are the shells of electrons where the electrons orbit. So just to remind ourselves that the mass of a neutron and a proton is 1. A mass of an electron is very small, so 1 divided by 2000 or 1800, depends what your teachers taught you. And that the neutrons, because they're neutral, have no charge, protons have a positive 1 charge, and electrons have a negative 1 charge. Now looking at the periodic table, just remember that the atomic number is the number of protons, and the neutron and the mass number is the number of protons plus the number of neutrons. And this will become really important when we now come to look at isotopes. You've probably met isotopes in chemistry, so things like carbon-12, carbon-14. Remember that these are atoms of the same element with the same number of protons but a different number of neutrons. If we look at carbon-12 and carbon-14 in the periodic table, they both have an atomic number of 6, which makes sense because they're the same element, which means that they must have the same atomic number. Their mass numbers are different though. Carbon-14 has 2 extra neutrons when compared with carbon-12. So when we look at radioactive isotopes, we're just talking about isotopes which are unstable and tend to give off radiation. So ionizing radiation may be given off an atom, and this is a random process, and it may give off alpha, beta or gamma radiation, and that's what we need to talk about now. So I'm going to start by chatting you through what alpha, beta and gamma radiation is, and then I'll show you some decay equations. So alpha radiation first of all. So what happens when alpha radiation happens is that 2 protons and 2 neutrons are lost from a particular atom, and clearly therefore you will have a new element whose atomic number, remember that's the proton number, is 2 fewer than it was before, and the mass number, because it's lost 2 protons and 2 neutrons, will have gone down by 4. With beta radiation, what's happened this time is that a neutron has turned into a proton and stayed within the nucleus of that particular atom. So because a neutron and a proton has the same charge, clearly the mass number will be unchanged, but the proton number will have gone up by 1, so you will have a new element. Now gamma radiation is very different because it's an electromagnetic wave, so you see no change in mass or atomic number. Do notice that alpha radiation is the largest, it has the largest mass because it is made up of 2 protons and 2 neutrons, and it is the most ionizing, whereas gamma is the least ionizing. And ionizing is just the ability to cause something else to become an ion, which is a charged particle. So if we compare the properties of alpha, beta and gamma, notice that alpha, as I've already said, is the most ionizing, beta is in the middle, gamma is the least ionizing. In terms of their penetrating powers, that's how easily they pass through substances. You notice that alpha is stopped by air, beta is stopped by aluminium foil, and gamma is stopped by several centimeters of lead or several meters of concrete. In terms of their range in air, alpha has a range of only about 5 to 10 centimeters, beta has a few meters range, whereas gamma has an infinite range in air.
The table shows the nature of alpha and beta particles. So alpha we know is a helium nucleus made up of 2 protons and 2 neutrons, and beta is a fast-moving electron. Explain why alpha particles and beta particles have different penetrating powers. So basically let's start by looking at the difference. So state first of all that alphas are much larger because they're made up of 2 protons and 2 neutrons, so they have a heavier mass, they have a higher charge. This means that they cause more ionization, which means they can't penetrate as far. And that's due to all the energy which has been lost as they've caused lots of ionization. And also point out that the alpha particles are more likely to collide with the atoms because they are bigger. Or you could give the converse argument for beta, so you could say they're smaller, they have less charge, they cause less ionization, they have a lower mass. So in this first alpha decay equation, let's have a look. We need to work out the new mass number and the new atomic number of thorium. So we're starting with uranium-238, that is its mass number. Well, I've just told you that you lose 2 protons and 2 neutrons in alpha decay, which means the mass number must have therefore decreased by 4, which is why its new mass number is 234. Because you've lost 2 protons, it means that the atomic number decreases by 2 to 90, and that is your answer. In the second example, I'm after the new mass number of lead, so we've lost 2 protons, 2 neutrons again, which is why the mass number will have decreased by 4 to become 212. And this time we're looking for the original atomic number or proton number of polonium. So we know that we've lost 2 protons to get to 82, which means the original atomic number must have been 2 more than 82, so the answer here is 84. In this beta equation, we're looking at what happens to sodium. So I've already told you that in beta decay, a neutron turns into a proton and stays within the nucleus of an atom. Because of that, the mass number is unchanged. So we're going to stay having a mass number of 22. The neutron turns into a proton and stays within the nucleus. And because of that, we have an increase of 1 on the atomic number, so that turns into 12. And because we've increased our atomic number, we clearly have a new element. And if you look in the periodic table, you'll see that the element with the atomic number of 12 is neon. So in this question,
we're looking for the new mass number and the new proton number again. So we have a neutron turning into a proton, meaning that the mass number is unchanged, which is why I'm going to write a 14 here. Because we've gained an extra proton, it means the atomic number will have gone up by 1, forming 7. And because you have a new atomic number, we have a new element, and that element, according to the periodic table, is nitrogen. Now we're going to be moving on to looking at half-life and background radiation. So let's first of all state what is background radiation. And it is radiation which is always present in our surroundings. And so you may need to list several sources. So that could be cosmic rays from space. It could be radioactive rocks like granite found in Cornwall. It could be food and drink, and medical sources such as X-rays. Now, what is the unit for measuring radiation? It is the becquerel, capital B, little q. And what instruments do we use to measure the level of radiation, whether that's background or not? We use the Geiger-Müller detector or counter. Do remember, if you're given a radioactive source and you need to determine its radioactivity, you must work out the level of background radiation and then subtract that from the value you get from your Geiger-Müller counter to make sure that you remove it from your calculations. So half-life, now let's define it first of all. Remember, this is the time taken for half the radioactive nuclei to decay, and you might have used coin tossing at school to help you model this. The reason why that works really well is because radioactive decay is a random process, and as is tossing the coin. And with tossing coins, you've no idea, you can't predict whether it will land on heads or tails, and it's the same with radioactive decay. You have no idea which of the radioactive atoms will decay first. In terms of using tossing a coin as a model, it does have several limitations, and this is really the number of times you can do it. I mean, realistically, probably at most about 1,000 times, whereas with radioactive decay, you're looking at millions of atoms which need to decay. And now I'm going to show you a question involving half-life, and I'll talk you through the half-life calculations because they're probably the most difficult part of this topic.
A sample of sodium-24 has an activity of 1400 becquerels. On the axis, sketch a graph to show how the activity of this sample changes over the next 40 hours. The half-life of sodium-24 is 15 hours. So at time equals 0, we're going to have an activity which is 1400. We know that the half-life is 15 hours, so look along 15 hours, half of 1400 is 700. So we need a cross there. When another 15 hours has taken place, so at 30 hours, that 700 will have halved again to 350, so we need a mark here. And now you can attempt to draw a curved line, which I'm appalling at. Oh, it's not too bad. Granite is a rock. It contains a radioactive isotope of uranium that decays very slowly. Explain how scientists can use this radioactivity to find the age of a piece of granite. So first of all, make a note that there is a known proportion of activity when the rocks are formed. This means that you can now measure the proportion of uranium now, and then you compare the activity of the original uranium's value with the activity now, and this can help you determine the number of half-lives which have elapsed, and then you calculate the age from reference to half-life. Suggests why the age of a piece of granite could not be found using uranium isotope with a half-life of 15 hours. And that's obvious because the half-life is too short. 15 hours has meant that the decay has occurred far too quickly, and so the activity now would be far too small to measure. Sodium-25 has a half-life of 1 minute. What fraction of it remains after 3 minutes? So what you have to do here is work out how many half-lives have occurred. And because it's 3 minutes and 1 goes into 3 minutes 3 times, 3 half-lives have occurred. And then all you have to do, because you're finding out a fraction, is do a half times a half times a half to find that 1/8 remains after 3 minutes. Question 3. Xenon-133 is a radioactive gas used for diagnosing lung problems. In 15 days, its activity falls to 1/8 of its original value. What is its half-life? So we need to work out how many half-lives occur to get to 1/8. So what you need to do is, you might have to do trial and error, but you need to just do as many half-lives as you need to in order to get to 1/8, and the answer is actually going to be 3 of them. So 3 half-lives occurred in 15 days. So how long did it take for 1 half-life to occur? Well, you just need to do 15 divided by 3, and the answer is 5. So 5 days is its half-life. Question 4. The half-life of the radioactive isotope sodium-24 is 15 hours, A sample has a count rate of 240 counts per minute. Its count rate 60 hours later will be... Okay, so this time, again, we need to find out how many half-lives have occurred. So I'm going to do 60 hours divided by 15, and I see that 4 half-lives have occurred. So, therefore, after 1 half-life, 120 counts would remain. But there were 4 of them, so I'm going to times it by a half 4 times. And that is the same as 240 times answer, and that is 15 as my answer. So its count rate after 4 half-lives have occurred, so I've divided 240 by 2, or times them by half 4 times, and I have got 15 as my answer. So that's 15 counts per minute. Question 5. A radioactive isotope of silver has a half-life of 20 minutes. A sample gives a rate of 6,400 counts per second at 9 o'clock. At what time will the count rate be? About 200 counts per second. Okay, this sounds hard, but again, just use trial and error to work out how many half-lives have occurred. So I'm just going to do 6,400 times a half, and I've got 3,200, so I'm going to times it by half again. And I'm going to keep going until I get to 200. And actually, what I found here is that it has taken 5 half-lives in order to get to 200 counts. So all I did was times 6,400 by a half 5 times, and I got to 200. So like I said, that means 5 half-lives have occurred, and each half-life took 20 minutes, so therefore 5 half-lives takes 100 minutes. So all you need to do now is work out what 100 minutes past 9 o'clock is, and remember there's 60 minutes an hour, so that brings us up to 10:40. That one was quite hard, but you can work it out. Like I said, just use trial and error to work out how many half-lives have occurred. Practice doing as many questions of these as possible in order to get good at answering the different types of question. Remember, when you're reading off graphs, to look at, you can read off the half-life by looking at how long it took for the counts to reduce by half, and then you need to read across to see how long that took. Take into account background radiation, because you'll see that the graph line will never actually touch the x-axis, and that's because background radiation exists. And remember that that comes from things like cosmic rays, x-rays, rocks, just general stuff really. And remember, half-life is actually the amount of time taken for half the radioactive nuclei to decay. So, after 42 days, the activity of a sample of phosphorus-32 has decreased from 400 becquerels to 50 becquerels. What is the half-life of phosphorus-32? So we've gone from having an activity of 400 becquerels to 50, so we need to work out how many half-lives took place. So there's the first one, which would have taken us down to 200 becquerels. The second one would have taken us down to 100 becquerels. And then the third one would have taken us to 50 becquerels. So we can see here that 3 half-lives have taken place. And what was our time frame? Well, 3 half-lives must have occurred in 42 days. So then it's a simple expedient of doing 42 divided by 3 to work out how long each half-life took. And that answer is therefore 14 days.
Looking at uses of radiation. Alpha radiation is used in smoke alarms. I'm going to chat to you how this works. So you have an alpha source in a smoke alarm, which is giving off alpha particles. And what happens is those alpha particles collide with air particles in the air, and they ionize them, creating a small electric current which is picked up by the detector. Now, I've already told you that alpha's range in air is very limited. So the moment there's a fire, there's now smoke particles in the air, and they obstruct the alpha and they stop it reaching the detector. So the detector gets 0 reading, and therefore the alarm goes off. Beta radiation is used in aluminium foil thickness, so kitchen foil that you wrap your sandwiches in. So there are 2 rollers, and there's a detector either side. So you've got a source of beta, detector on the other side, and there's a certain amount that should be picked up. And if that detector reading is too low, it tells you that the aluminium foil is too thick, so the rollers press together to make the foil thinner, and so the detector can pick up the correct amount. In terms of in use in medicine, do remember that we use radioactive sources in medicine, such as radioactive iodine, and we call this a medical tracer, and that's because it's used to diagnose things like kidney problems. So the patient takes a sample of radioactive iodine, it flows through their body, and there's a detector which picks up how much radiation there is, and you'll see a characteristic graph reading where the reading stays high, and that tells you that there's a blockage within the kidney. So they do make great diagnostic tools. Do notice some crucial properties though, and that is that you've got to have an isotope which decays into a stable product, which makes sense because you don't want it giving off radiation. It has a medium-sized half-life. You don't want it to have such a short half-life that you can't actually pick up how much there is because it's already decayed away, but you also don't want it to be so long that you're staying radioactive for many years to come, because that is dangerous. And this is because of all the dangers relating to radiation. So remember, ionizing radiation causes mutation within our cells, and mutation is the first step leading towards cancer. So it's pretty nasty stuff. We can reduce our risk and limit our exposure to radiation by wearing protective clothing, by standing behind lead shields, by using tongs to handle the radioactive material, and for using things like photographic film. You see these in little medical badges that radiographers wear, and that will show up if they've been exposed to too much radiation. Looking at use of radioactive carbon, so carbon-14 in carbon dating, so that's when you determine how old plant material is, for example. So carbon-14 is radioactive, and during a plant's lifetime, remember when it photosynthesizes, it takes in carbon dioxide. So a certain proportion of the plant will contain carbon-14. Now once it dies, clearly it won't be photosynthesizing anymore, and over time that radioactivity decreases. And by comparing the radioactivity of a sample with the radioactivity of a living version of that particular plant, you can work out how old it is. That's a very clever dating technique. So nuclear fission, let's be very specific with our definition. Remember that it is the splitting of an atomic nuclei. Do say atomic nuclei. If you don't say that, you don't get the mark. So where is this carried out? It's carried out artificially within a nuclear reactor, which means we need to add a fuel, and we tend to use uranium-235. So we have our nuclear reactor which contains uranium-235. To get the nuclear fission process underway, we have to fire a single neutron at that uranium nuclei. The uranium nuclei splits into two daughter nuclei, and I'm being very specific with my wording, and you should be using this exact wording in your exams, releasing 2 to 3 neutrons. These go off and collide with other uranium nuclei, which split, forming 2 more daughter nuclei, and 3 more neutrons are released, and before you know it, a chain reaction has been set off. And this can obviously become extremely dangerous if it isn't controlled, hence the Chernobyl disaster back in the 80s. So how do we try and improve the safety of the nuclear reactor? Well, we have several mechanisms, such as control rods. These dip into the nuclear reactor, and what they do is they absorb neutrons. So clearly, if you take away neutrons, they can't collide with any uranium, so the whole reaction slows down. You also have a moderator, and what a moderator does is that it slows the neutrons. Notice the difference. Control rods remove neutrons, moderators slow the neutrons, so they lower the kinetic energy, meaning that they collide with less energy, and therefore subsequently the reaction is made safer. You might find there's a coolant, and that's just cold water, which removes some heat from the reaction. And you'll also see that it is contained within a big lead box or concrete, and that's to improve the safety, to make sure that people that work in the nuclear reactor don't get exposed to radiation. Now, the type of energy released is going to be kinetic energy, and the kinetic energy is converted to thermal energy, which is used to heat water. That water turns into steam, and steam turns the turbines, and the turbines turn the generator, and that's how the electricity is actually produced from a nuclear reactor. There are disadvantages, although this is a great way in which we can produce electricity, because you only need a very small amount of uranium in order to generate huge amounts of electricity. It is extremely dangerous. The radioactive waste remains radioactive for many years. It needs to be stored safely underground and make sure that it can't contaminate water sources which we drink. It has high decommissioning costs, and that's to do with how you actually take apart the nuclear reactor once you're done with it, and that's obviously due to the safety aspects. And it also has high startup costs, so building it in the first place will be extremely expensive.
11. In a nuclear reactor, uranium-235 nucleus absorbs a neutron and fission occurs. Complete the equation below that shows a typical fission reaction. Please don't find this totally overwhelming. We can work it out. So we've got uranium-235 going in, and a neutron is fired at it, leading to, I think that's barium and krypton being produced as the smaller nuclei, and 3 neutrons given off. So basically, it's like just like maths or algebra or something. You just need to make sure that whatever you started out with, which was uranium-235, everything else produced after that has to add up to 235. You can't just randomly lose matter. So effectively, what you need to do is add 142 to 1, and also to 1, because that's the neutrons accounted for. And then if you add those all up and take them away from 235, you'll get an answer which is 91, and that needs to go here. And then the same below, you've got a proton number, an atomic number of 92, and we can see 0 against the neutrons, so all we need to worry about is the krypton, 36. So just do 92 take 36 and you'll get an answer which is 56. B. Explain how nuclear fission can lead to a chain reaction. So for the first mark you want to say that the neutrons are released, that these are then absorbed by other uranium nuclei, and this causes further fission reactions. For another mark you could have said that neutrons are slowed by the moderator, but I don't really know why you'd think to write that particularly. C. The diagram shows a nuclear reactor. On the diagram, label the control rods and the shielding. So the black things hanging down here are the control rods, and the shielding is the box on the outside, which prevents excess radiation getting out. Explain why shielding is needed. You need to talk about the fact here that the reactor material or the waste is radioactive, and then for the second mark, that can lead to cancer, which is very dangerous. So that's why you obviously need to shield it and keep it away from people. And the reason why you do need shielding is because remember that radiation is very penetrating. It will pass through a huge amount of air, so you do need that concrete box around it to prevent it getting out. 12. The diagram shows the main parts of a nuclear reactor. So we've got our control rods, moderator, fuel rod, shielding, reactor vessel and coolant in. Do remember the control rods absorb excess neutrons, and the moderator removes the kinetic energy, and the moderator reduces the kinetic energy of the neutrons. The fuel rod will obviously provide the source of uranium. Anyway, draw a straight line linking each part of the reactor to its correct purpose. So I've already accidentally said what the control rod does, which is that it absorbs neutrons. I'm going to go to fuel rod because that's the next easiest one to answer. Remember that contains uranium. The moderator, I said, decreases kinetic energy, which is the same as slowing them. The reactor vessel keeps radioactive material inside the reactor. That makes sense. So the coolant transfers thermal energy. That also makes sense. Which of these is a nuclear fission product? So remember that's what is made after nuclear fission takes place, and remember nuclear fission is the splitting of the atomic nuclei which releases neutrons, which is why C is the answer here. Describe the process of nuclear fission. So a neutron is fired at the uranium-235 nucleus, and the nucleus splits, producing 2 daughter nuclei and up to 3 extra neutrons. And I've actually already said 3 or 4 marks worth of things, and you can say that kinetic energy is released. State 3 ways in which nuclear fission differs from radioactive decay. So remember, nuclear fission is a human artificial process, whereas radioactive decay occurs naturally. So start by saying that decay is a random process which occurs naturally, whereas fission is not random. It's due to humans firing neutrons at uranium-235. You want to talk about the fact that fission produces 2 daughter nuclei, whereas decay only produces 1. And remember that alpha and beta or gamma are produced by decay, whereas in nuclear fission neither alpha or beta or gamma are released. Instead, it's simply daughter nuclei and neutrons. So let's start by looking at the solar system. So the solar system contains all the planets that you guys have heard of, and in order, starting closest to the Sun, you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and sometimes people count Pluto, but I don't think we're supposed to count it anymore because it is too small to be counted as a planet. You saw me doing my thing of remembering this. The way I remember the order of the planets is my very easy method just speeds up naming, and that is a great mnemonic for helping you remember the order of the planets.
Now, more terminology, we need to look at things like the galaxy. A galaxy is made up of billions of stars, so it's a collection of billions of stars. What is the universe? Well, the universe is made up of billions of galaxies. So we on Earth are living on a teeny tiny planet which exists in a galaxy. The galaxy you do need to know the name of, it's the Milky Way, and the Milky Way is just one of billions of galaxies which make up our universe. So yeah, it's kind of mind-boggling. I try not to think about it too much because it freaks me out. Now, what holds all the planets in position? That is gravitational pull, and that's what keeps everything in position. So for example, it keeps planets orbiting the sun, it keeps moons orbiting the planets, it keeps artificial satellites orbiting the Earth, for example, and lastly it keeps comets orbiting the sun. Do remember that a satellite is any object which orbits a planet. There's both artificial and natural satellites. Artificial ones are ones which are man-made, that we have placed into the sky, whereas a natural one is one such as the moon. Now, comets, as with planets, have elliptical orbits, which means they have an oval orbit. They don't have a perfectly circular one. But the thing you'll notice with comets is they have very elliptical orbits, like a very squashed circle. And what that means is the comet travels fastest when it's closest to the sun due to increased gravitational pull, and travels more slowly further away from the sun. Now, what dictates the strength of the gravitational pull? That will be both the mass of the planet in question, so larger planets have a stronger gravitational pull, and also the distance from the sun. So the further away a planet is from the sun, the less strong the gravitational pull will be.
The diagram shows the orbits of some objects in the solar system. Path X is the orbit of a, so if you have a look at its path, it is pretty much circular, which means it can't be a comet. It's orbiting the sun, which means it must be a planet, so that is C. Path Y is the orbit of a, so we've got an extremely elliptical or oval orbit, which sometimes takes the object close to the sun and other times takes it really far away, and this is characteristic of a comet. And the objects are held in orbit by, remember this is gravitational force, which is option C.
We now need to look at the life cycle of stars, both very large stars and stars which are smaller, like our sun. First of all, we need to understand the term nebula. Now, a nebula is just a big cloud of dust and gas, and that's the beginning of a star's life. We're going to take a small star to begin with, such as our sun, and we're going to look at its life cycle. So to begin with that nebula, that big old ball of gas and dust needs to be brought together. How? Through gravitational pull. So it pulls together all that dust and gas, and then at that point it can start burning fuel, and the fuel in question is hydrogen, because the hydrogen nuclei come together. We call that nuclear fusion because they're fusing and they release a huge amount of both light and thermal energy. At this point, the star is in its main sequence. It's like the adult part of its life. It will eventually run out of hydrogen fuel and it will start burning helium, and then it will swell up to form a red giant. Then at this point it turns into a white dwarf, and then when it totally runs out of fuel it will turn into a black dwarf. Large stars, so very, very large stars, have a slightly different life cycle. They start in the same place, which is that they have a nebula, so the huge dust cloud, gas cloud, will be pulled together through gravity. Then it will enter its main sequence and will start burning through its hydrogen fuel. Again, nuclear fusion is occurring. However, this time when it runs out of fuel, it will turn into a huge red supergiant, and then at this point a huge explosion occurs called a supernova. I love that word. And then dependent on the size of the star, it will either form a neutron star, and if the star is very, very massive, it will form a black hole, which you've probably heard of from films. Very hot stars appear blue, and the cooler stars appear red, and the middling stars appear orange. Now, the brightness of the star, this is just for triple people only. Now, it's dependent on three things. First of all, you can talk about the absolute brightness. Now, when you look at the brightness of a star, it's a bit like looking at the brightness of a car at night. Now, you might look out of the window and see various cars going past and think that they're different brightnesses, but the fact of the matter is you can't look out and decide that car's lights are brighter than another unless you know how far away they are, because clearly a car which is further away will have dimmer lights. One that's basically on top of you will look very bright, but you don't know that that bright car light is actually brighter, and that's why you have to compare all of the brightnesses from the same distance. And this is also true when you look at stars. Now, that's when you compare all stars as if they were the same distance away from us, and that's the fairest way of looking at the brightness of a star. You can also look at how bright a star is from the Earth, and we call that the apparent brightness. So that's not a true reflection of how bright the star is, it's just looking out into the sky and looking at how bright the star is. And lastly, you can look at the luminosity of the star, and that's a measure of the amount of light energy given off a star every second. We need to touch briefly on the Hertzsprung-Russell diagram, and I promise it's not as complicated as it looks. It's merely a way of comparing the luminosity of a star with its surface temperature. So if you look at the diagram, going up the y-axis, we can see increasing luminosity. Across the x-axis, we can see that the temperature of the star is increasing. So if you know both the luminosity and the temperature, then you can plot on this diagram where the star is, and you can also work out at which point of its life cycle it is in, so whether it's in its main sequence or about to approach a supernova, for example. We now need to look at the Big Bang Theory. Now, please don't argue with me if you're really religious and you believe that there was a different way in which the Earth and everything around us became created. I'm just trying to teach you a physics video, and from a science point of view, you need to know that the Earth and the solar system, and basically the whole universe, originated from the Big Bang. And what that means is that all this dust and gas all started together at one very particular point, and then there was a huge explosion, the Big Bang, which sent it all whizzing out into space and formed the various millions of galaxies that we know exist in the universe today. Now, the Big Bang Theory has two pieces of evidence which support it. Firstly, CMBR, which is cosmic microwave background radiation. Now, if they take a photograph of space, they find that there's radiation scattered evenly throughout space, and the only way that they can decide that that occurred is due to it all beginning life in one particular place, and then the Big Bang caused it to spread out evenly throughout the universe, which is why they believe CMBR provides good evidence for the Big Bang. Next, we need to look at redshift, and to understand redshift, we need to understand the Doppler effect. Now, the Doppler effect applies to any type of waves, so we're going to look at both sound and light waves. Now, you might be aware that if you're sat in a car and an ambulance goes past you, its siren changes from being very high to lower, and that's due to the Doppler effect, because if you imagine that sound wave as it reaches your ear, as it goes past you, as the ambulance zips off into the distance, that wave gets longer, so its wavelength increases. And then if you actually think about your physics and what you understand to do with sound waves, remember that the wavelength relates to the pitch of a sound. So if a wavelength is longer, the pitch decreases, so the sound sounds lower. If the wavelength gets closer together, then you get a higher pitch, so it sounds higher. So that ambulance is moving off, the wavelength is increasing, so it sounds lower. Now, we can apply this to space, specifically galaxies. So we think that galaxies are moving away from us. So those galaxies we can see in the sky, well, we can only see the Milky Way because that's the galaxy we're part of, but very strong telescopes can tell us that the galaxies are moving away. Now, the light that is being emitted from stars in those distant galaxies, it reaches us on Earth. Now, clearly, if the galaxy is moving away, that light wave, its wavelength will increase because the whole wave is stretched. So the galaxy moves away and that wavelength gets longer. Now, if you actually look at the visible spectrum, you will see that when the wavelength gets longer, the light becomes redder, and we call this redshift, which is why redshift is evidence for the Big Bang Theory, because the Big Bang Theory supports the notion that galaxies are moving away from us. Now, if that light appeared bluer, again, if you look at the colour spectrum, it would mean that the galaxy is moving closer to us because the wavelength would have gotten shorter. So I hope this is making sense to you. Do have a look in your textbooks, but both redshift and CMBR provide good evidence for the Big Bang Theory. Now we're going to look at the Doppler equation using an example to help us. So, light emitted from the sun has a wavelength of 435 nanometers. A faraway galaxy emits the same light, but owing to the Doppler effect, has a different wavelength of 492 nanometers. Calculate the speed of the galaxy. The speed of light is 3 times 10 to the 8 meters per second, and state if the light has been blue or red shifted and why. So obviously, first of all, we need the key equation, which is this. I write it out in words, it's way less confusing if you have it in words. Otherwise, it's just a load of symbols that don't really mean very much. Written out the equation, let's have a look at what we've got. I know that we're calculating the speed of the galaxy, so this value up here is x. Speed of light has been handily given to us, which is 3 times 10 to the 8.
Looking at the change in wavelength, well, this is the reference wavelength, this is the new wavelength, so change means the difference between those two numbers. So let's just write it in like this. We'll have to work that out separately. And then lastly, the reference wavelength, well, that will be the light emitted from the sun, is 435. So that's everything we need. Let's do our interim calculation. So 492 minus 435 equals 57. 57 is the change in wavelength over the reference wavelength, which is 435, equals x over 3 times 10 to the 8. Let's sort out the left-hand side first of all. So do 57 divided by 435, giving us 0.131. Just write out that whole number, because when numbers are this small, if you round too early, you're going to make it incredibly inaccurate. So just keep it nice and written out. And then to get x by itself, you need to times both sides by 3 times 10 to the 8. And it gives us this pretty large number, which again, I'm not going to attempt to read out. And that's meters per second, so that's your final answer. State if the light has been blue or red shifted and why, so we just need to compare the two wavelengths. So the faraway galaxy is emitting a much longer wavelength, which is 492 nanometers compared with 435. Because that wavelength has increased, we know that the light has been red shifted. So now I need to talk you through the orbital speed part of the paper. I'm just going to do the whole of this question because it's all relevant. This question is about planets in the solar system. Planets in the solar system have different sizes and masses. The bar chart shows the gravitational field strength of each planet compared to Earth. And we can see Jupiter has the largest gravitational field strength, which makes sense because it's the largest planet, therefore it has the largest mass. So in order to answer this question, remember the equation weight equals mass times gravitational field strength. The mass is staying the same because if you look at all the options below, they're all 1 kilogram. So it's just a matter of using the graph to work out which gravitational field strength is the greatest. So let's look at option A. A 1 kilogram mass would weigh more on Venus than on Neptune. Have a look at the graph. That's incorrect. A 1 kilogram mass would weigh more on Earth than on Uranus. That is correct because the bar for Earth is slightly higher than that for Uranus. But as all good scientists should do, keep checking the final two options. A 1 kilogram mass would weigh more on Mercury than on Saturn. That is incorrect. A 1 kilogram mass would weigh more on Mars than on Jupiter. Also incorrect. On Earth, the gravitational field strength is 10. Which of these is the value for the gravitational field strength on Mars? We know that the gravitational field strength for Earth is 10, and we use the graph and we can see that it has been given as 1. So obviously 10 is 1 times 10. So we need to do the same calculation when we're looking at Mars. So read off, we can see it's 0.4 multiplied by that 10, and that gives us a value of 4. Deimos is a natural satellite of Mars. Deimos has an orbital time period of 1,820 minutes and an orbital speed of 1,350 meters per second. Calculate the orbital radius, and we've been given the time period and the orbital speed, so I like to underline those and just have a quick look down here. We're in meters, so we're looking at standard SI units everywhere. And this here needs converting because minutes is not the standard SI unit, so obviously we need to convert that to seconds by doing 1,820 times 60 to get 109,200. Then we're going to write this equation, V equals 2 pi r over t. So V stands for orbital speed, r is for the orbital radius, t is for the time period. It's a matter of substituting in numbers. So we know that the orbital speed is 1,350, 2 pi, we're looking for r. We've worked out the time period is this number. So how do we get rid of that 109,200? You have to times both sides by it. So times by that on both sides. And that means 1,350 times 109,200 to get this very large number, which I'm not even going to attempt to read, equals 2 pi r. To get r by itself, just divide both sides by 2 pi. So keep that number in your calculator and divide by 2 pi, and r will therefore equal this large number again. And it's up to you how many significant figures you want to give it to, seeing as they haven't specified, so I'm going to write it like this. The diagram shows Deimos in orbit around Mars, which arrow shows the direction of the force of gravity that Mars exerts on Deimos. That would be like this. So it's A. And that's because Mars is attracting Deimos, the moon, to itself.
So we're done. Well done for staying all this way. I'm really impressed if you managed to watch the video all in one. Don't forget about my revision guides. My perfect answer revision guides are available on my website right now at www.sciencewithhazel.co.uk. You can click on this card to buy yourself a copy of my revision guide, which makes the perfect accompaniment to these videos.